I request all the delegates and participants to occupy their chairs in the auditorium hall. Please make sure that your mobile phones and other electronic devices are switched off or silent mode during the workshop. Good morning, ladies and gentlemen, esteemed guests and workshop participants. Welcome to second day of GIAN workshop on advanced functional material and green energy strategies. I once again welcome Professor P.V. Kamath sir. We are delighted to have back for another day insightful lectures as we continue our GIAN workshop lecture series. As you may recall, we were fortunate to have the privilege of listening to a thought-provoking and inspiring presentation by Professor P.V. Kamath sir yesterday. He captured us with his informative presentation. Ladies and gentlemen, please join me in welcoming back Professor P.V. Kamath sir for today's lecture. This session will be chaired over by Professor S.P. Hanvirgekar sir, Department of Chemistry. May I invite Professor S.P. Hanvirgekar sir to take a charge and continue.
Good morning to all. I welcome to all of you in the second day of this GIAN workshop. I also welcome to Professor P.V. Kamath sir, who is going to deliver a lecture on directing energy and electron transfers in semiconductor nanomaterials. So, sir, please take a charge of today's this session and start your. Yes? Yet nahi awaaz? Okay. Thank you. Sir.
Light energy, and we want to use it for energy conversion, right? So in the energy conversion, it's a three-legged stool. You need three parts. One is capture. You need to capture those photons, right? Sunlight. Then you need to convert it, light into chemical energy or light into an electrical energy. When you convert light into electrical energy, we say photovoltaic, right? You are converting photons into electrons. Now things like photosynthesis, where the plants do much smarter, they do, right? So they capture the sunlight, and then after capturing, they are converting it into chemical energy. The chemical energy is what gives us the food. All your carbohydrates, right? If a plant is producing some beans, that is carbohydrates. How did it form? That is the beauty of the photosynthesis. There is a thing called photoreaction center in all these leaves. They take it, carbon dioxide and water. Those are the only two chemical reactants. They combine the two in such a way to make carbohydrates. If you see the formula of carbohydrates, it's C, H, and O, depending upon how many units you have. That's the beauty of the photosynthesis. And we have been trying for more than 50 years to mimic this one. And one of the Nobel Prize got was Melvin Kelvin. And it is known as the Kelvin dark cycle. So in the light, the chlorophyll absorbs light, but there is what they call energy transfer process. So they are absorbing. Why the leaves are green? Blue and red, right? So it absorbs blue and red light. So the blue light that is absorbed gets transferred very quickly to become the red light within the thing. If you ever want to try it, one nice experiment, take the outside grass, put some alcohol in your lab and mortar pestle, just grind it. You get a light green juice. Put it in a quartz cuvette and shine with a UV light. You will see bright red fluorescence. Okay? So these kind of photoactive materials are there. But when it is there, it doesn't glow because it is transferring energy and then doing electron transfer. Because you have to reduce CO2 into carbohydrates. So that is the electron transfer process. So today, we want to artificially do it. So we want to understand using semiconductor quantum dots, trying to do the similar process of energy transfer and electron transfer. And these materials have that property. And how do you understand that properties? And we have been looking into it. Okay, this is our recent work. This is going to be a little more specialized. So I hope you will excuse me for doing it, not having elaborate introductions and those things. So, okay, so again, these are the people currently working in our group. They are the one doing it. So this is the reaction center I was talking about. So this energy transfer, the shine comes in. These are the chlorophyll reaction centers. And then they hop this energy from one to the other. So that is the one, the pigment molecules, and then it goes to this electron transfer. So the nature does it so beautifully, this energy transfer and electron transfer coupling together to give us the carbohydrates. So without that, we will not be surviving, right? So this is one of the major things. And we have been trying to do it in the past, trying to take a TiO2 and a square-end dye and a cadmium selenide. We have tried and transfer what they call FRET, Foster resonance energy transfer, to this dye, and this dye can inject electrons and you can make it. So these are some of the strategies we have tried. People also use energy transfer in bioimaging. They deliberately put some kind of a cyanine dye to see, and based on this energy transfer process, they can tell you the distance between the two groups. So that is very there. So when you shine the light, you have your species, now energy donor and energy acceptor, right? But when you transfer energy, there are two things. One is called singlet, another is triplet. And typically, the spins are opposite in singlet. And when you excite it all the time, it's a singlet excited state. But it can come down to triplet excited state, but directly from this one to this one is forbidden. It doesn't happen. It has to come from this one to this one. So this one flips around to become triplet. So there are two different excited states. This has a more energy, this has a lower energy. And this one has a short lifetime, this one is a long lifetime. When you see these glows of any dye molecules, that is most of the time it is singlet. The triplets you don't see it unless a long time, but they can phosphor, so you can see it for a much longer time. So that is there. So the same system can also undergo electron transfer. You can do reduction, you can do oxidation. Isn't it interesting? The same semiconductor nanocrystal can either transfer energy or electrons, right? So here is the energy. It can either transfer singlet or it can transfer triplet, and the mechanism could be Dexter or Foster type. And on the same token, the same material, same quantum dot we are talking about, can transfer electrons or holes. And this is a chemical reaction. This is not. This is just transferring energy. So this is actually, you are doing a chemical. What ultimately we want to do is couple these two processes in a way that we can do it. Right now we have not succeeded in coupling the two. What we have done is trying to look for systems to understand why these guys transfer singlet or triplet, what is the mechanism. Understanding that one can help better. This one is probably widely studied in literature. You might have called photoelectrochemical water splitting, right? So that's the semiconductor absorbs light, reduces the hydrogen ions to give you H2. Holes can oxidize to give you O2. And there are a lot of materials have been designed. Sometimes people apply bias, sometimes they use heterostructures, various different things. Those are the electron transfer reactions, okay? So we are not going to do any water splitting today, but we are trying to understand the processes that control. And this also gives you an opportunity how to study these processes, okay? Don't go into details, but think about how to study these ones, sometimes simple. One of the applications currently that is being studied is up conversion. That means you take a low energy photon and make it a high energy. As I mentioned, a lot of these infrared photons are not utilized. And if we can design some system that can capture that one and make it is higher energy photons, again, we are not gaining energy. You need two low energy photons to get one high energy photon. And the mechanism that is proposed is like the cesium lead iodide nanocrystal, which absorbs about 800 nanometers. It can transfer energy to generate ruberine triplet. Ruberine is a dye molecule. And that dye molecule, now the two triplets come together and form an excited singlet. And then they transfer it to this called a perilene dye. And that gives you 640 emission. And people have just, you mix these three, the cesium lead iodide, ruberine, and DBP, and make a film. And shine with a laser 800 nanometers, you see a fluorescence of 640. Okay? The magic happens, right? But now the question comes, how are these processes? Can you identify individual processes? And we are working on it, but before that, we started to study these energy transfer processes. And that's what I'm going to talk is energy transfer to rhodamine dyes. Okay? Just take two examples and study how it is. And the rhodamine dyes, one of the popular one is rose Bengal, and that is the red dye. There is, again, it's a derivative here. They have got different functional groups. This is the isothiocyanate, and this is the rhodamine B. They do have different absorption, I will show you. And in the second part, I will talk about electron transfer process. So let's sort out first energy transfer and then electron transfer processes. Okay, what we are trying to do is excited state. And here you can see here, yesterday I mentioned briefly, if you have a perovskite nanocrystals, the only thing you have to do is change these halides. And they're easy to exchange. You just expose it to bromide to either chloride or iodide, it suddenly changes. So this is the band gap of this material. So this is, I think, about close to 1.8-ish electron volts, and this is about 2.3, and this is higher, about 3. So they have different energies. So that means this one has a higher energy than this one. So we are taking the one in between, cesium-lead bromide nanocrystals, right? And then we are adding a dye and see how it interacts. And we are trying all 3 dyes, okay? So now let's start the experiment. The first thing you do is excitation wavelength. Okay. And then what do you record? Emission spectrum. And where does the emission spectrum come? It's always lower energy, right? Where you excite. So, I don't know. Oh, the projector is gone. How can both can go? Okay, it is a convenient tool because I told you that excited singlet state, the photon goes up and then it emits light. So you can basically characterize the excited state by doing this fluorescence emission. And that fluorescence emission tells us what is the energy that we are seeing. And he said it's 510 nanometers, but he's exciting at 360. So that 510 nanometer tells you the excited state level with which this energy is transferred. And then what is happening is it also gives us idea, then we can bring in our dye molecule, right? So we increase the dye molecule. In this case, we are doing cesium-lead bromide emission, and we are adding dye molecule. And we selecting the excitation wavelength such that it is exciting only cesium-lead bromide and not the dye. At 400 nanometers, the dye does not absorb. So when you shine the light, now you see the recording, the emission spectrum. Soon, hopefully, it will come. The emission starts decreasing, okay, as you add more of this dye. So why did it decrease, the 510 emission? That because those energy that is there, they were recombining. Now that energy got transferred into the rhodamine dye. So that's what, and we can watch that rhodamine emission going up in the next slide. So you need a new cable. Try to find a new cable. Okay. I think the cable is bad. No, it's fine. Yeah. Hey, do you have a mortar pestle and ethanol
Yeah,
and a black UV light? No.
black UV light.
Yeah.
I
Organic
will check
chemist.
for black UV light, but we have more quickly.
Yeah, because we can show you this. It's grass. That thing is very interesting experiment.
Okay, I will.
Yeah, but if it is a black light only, we need a black light too.
Okay.
That UV light, just to. And we need a quartz cuvette, so we can,
Yeah.
or any glass is fine.
We have parts. No problem.
Yeah, yes. It's a cable. It's not the laptop problem. It is a cable. You need a new cable. They need a new cable.
Otherwise, we can sit there.
Yeah, I'd sit there.
Okay. What are the things you need?
No. Don't worry about it. It's okay.
Otherwise, okay.
No, it's fine. If students want to show it, I can show it. It's very easy. It's okay. Don't worry about it.
No, they will bring.
It's just mortar pestle, ethanol and black light and a cuvette.
Yeah. These are the four, na?
Yeah.
Yeah. Ethanol, mortar pestle, black UV,
Yeah.
and quartz.
Yeah.
Okay.
And pipette to just put it in.
Yeah.
The pipette.
Yeah. Keep it.
Like just something to drop it, like
Or dropper.
yeah, dropper. Yeah.
मला पेपर देतो टिश्यू पेपर सध्या कॉपी करायला पाहिजे लगेच ओपन कॉपी पेस्ट करायचं हां कॉपी केल्याशिवाय सर ते पेन ड्राईव्ह पहिले कॉपी पेस्ट करून एक मिनिट
Something broken here somewhere.
yes just wait
3 minutes.
एक मिनिट थांबा एक मिनिट केबल पेपर पीसी बदलला ना 2 मिनिटं काम होतं इकडे आहे ना तो अजिबात काय हालचा नाही इकडं कोणाला येऊ पण जाऊ
For that EV, we have that small box.
Then
It doesn't work.
it works, but we have to bring it here. It is just to shine.
Yeah. Yeah, they're very.
Okay.
Sir, just check.
Okay. Okay. So we are back in business. Okay, so we want to study these ones. I just mentioned earlier, we have a molecular system like dyes where you have singlet and excited singlet. And when you shine the light, you see the emission. You know, all the glows you see everywhere. In the semiconductor, we have very similar situation. We call it conduction band and valence band. This is, you excite it, they radiatively decay, that's the glow. And this is non-radiative decay, that is, doesn't do, just makes it heat. And then there are trap states. And the trap states are very similar to triplet in the sense they are very long-lived. Okay? So this is just to give a comparison between the two. There are well-established theories here. They go mono-exponential decay when you do it first-order kinetics. And you can diffusional quenching of the excited state in solutions. Here, theories and processes continue to be explored. There are a lot of new things come up. This decay, when you see it, it often multi-exponential. So you cannot single process occurring. Defect states. Here, what is there on the surface matters. So that's where the problem. So what we want to now do is make this, combine the two. And now you see the complication in trying to understand these processes, right? We'll try to simplify in that sense. So again, we make the cesium-lead halide nanocrystals shown here. Again, it is a hot injection method, same method which got Nobel Prize, called hot injection. Here you use it, chloride, bromide, iodide. They have different band gaps. Here is 1.99 volts versus 3 electron volts for the chloride, right? So they are, if you look into the microscope, they are nice cubical structures, cubes. You see it, beautiful. And so again, there is a lot of people have been studying these kind of quantum dots. And I went to this one earlier to show you how the energy transfer processes and electron transfer processes can occur. And we are now studying this energy transfer process. For that, we studied 3 dyes, and we are adding now. So now we want to see whether it's singlet or triplet, right? Both are favorable from here. But it turns out when you take this cesium-lead bromide solution, you see this very sharp emission at 510. Okay? We are exciting at 400 nanometers so that this dye does not absorb, so only cesium-lead bromide. And if you look very closely here and zoom it, you see that as this one decreases, this emission increases. So that means we didn't lose that energy when this one went down. It only got transferred to this one, right? So from a green emission, we made a red emission. It's not a big deal because it's a downhill conversion, right? So that's what it is. And we use that double reciprocal plot I mentioned yesterday, and we can calculate the apparent association constant for this process, like how strongly these dyes are bound. Depends, because if you use this concentration here, they're typically of the order of 10 raised to 6. The rose Bengal absorbs much strongly, which has iodide groups around it, and this one sort of a weaker. So there is about a factor of 20, 2 orders of magnitude difference between the association constant. Let's see how it affects later on too. Okay, so you might say that, well, this dye also emits, so maybe some light is sneaking through in this one. So, but what we did was we switched it, right? We have the dye solution here, and now you added our donor. It is donating energy, right? We increase the concentration. And sure enough, when you add it, to begin with, we had a very weak emission. And as you started adding, it started going up. But now this is constant. But we are adding this one. So this increase of this dye emission should be coming from a donor species, right? It proves our point that this is what it is happening. And if you record the intensity height, and you can see here it is growing with more addition of this crystal. So again, it proves that it is coming from this one. Okay, now the question is whether we are seeing singlet or triplet. As I said, triplet is always at a lower energy. That is this dotted line. That's called phosphorescence. This is called fluorescence. So this one is much higher. We see only this band here that's corresponding to here. We do not see any triplet. So here, that means this path is not favored, it goes into singlet. Okay, so we'll come back to later why it is only singlet, not triplet later on. But for the time being, we do it, and we did the same thing for other two dyes. We see the same behavior of increase in emission whenever you add this cesium lead bromide to this dye. So this is one way to look into the energy transfer process using a simple your emission spectrophotometer. Okay. So now we want to see how fast this energy is transferred, right? So in the previous slide, you know, well, we see this emission coming up, but how fast is this process that going from this to here? So what we do is we call, again, I mentioned about transient absorption spectroscopy. We can put our sample here, bring a pump laser, we have a 400 nanometer laser pulse, and then delay the probe pulse and find out the spectral change, right? So the first, when it comes at the same time, you see this strong bleach of cesium lead bromide. And then you delay this pulse and record different spectrum here. So what you're seeing this negative bleach is the disappearance of the ground state. So it is trying to come back to the ground state, and we can follow the recovery. If you look into in the presence of the dye, this one recovers and this one grows in. Okay, so again, exactly same thing what we saw in the emission spectrum. One is decaying and one is growing. And now you can take a cross section and find these values versus time, because these were recorded different times, and you get these time scales. You can get the kinetics of energy transfer. And if you see it, this is the decay or bleach recovery here that is coming back and recovering. And this is the growth. Don't they look similar kinetics, rate-wise? Same time scale. That is the time scale with which its energy is transferred. We can follow the donor or we can follow the acceptor. So it gives an idea how fast this energy transfer is occurring in this system. Moving forward, we did with other dyes, very similar one, the recovery of this the cesium lead bromide in presence of 3 different dyes, and also the growth. The rhodamine B was the slowest and rose bengal was fast. And you can see the rate constants here given in terms of this one. And then what happened was we wanted to find out what is the mechanism. So there is 2 mechanisms that people give it. This is more common, Foster type. Another one is Dexter type. Foster type is a resonance energy transfer. It's a dipole-dipole coupling occurs. And here, actually, you transfer electron and holes. And what we did was there is an overlap of this donor emission and acceptor here, right? And then you see that's the overlap, and that is called J in these expressions. So we can calculate. So what we did was to the cesium lead bromide, we shifted the band energy, right? If you spike it with chloride, its emission starts shifting, band gap increases. But there is a less overlap. That means if it is Foster type, we should not see any emission transfer because there is no coupling between the two. And that's what we would expect in a theoretical way from the Foster type. This should drop down very quickly. But in practice, we see this one. So that tells us that probably both of these mechanisms are operating for doing this. So this is another way of proving. So doing this. Okay, so that's about is singlet energy transfer, right? So now, what about the triplet energy? We haven't done it yet, right? For that, what we did was we moved all the way to the cesium-lead iodide. So this is how between bromide and iodide you can shift the band gap. So all the way we came to this region, okay? So now what is happening is this energy cannot transfer singlet. It is too high. So this gap is smaller than this gap. But it can transfer to triplet. Does it quench? So we did the same type of quenching experiment. As you can see here, that's your rose Bengal absorption spectrum. This is the emission spectrum of cesium-lead iodide. Remember, the previous earlier I mentioned was cesium-lead bromide. That was having an emission at 510. But here now the emission is at around 700 nanometers. And this cannot transfer energy here. That's a higher energy, right? So, but we still see quenching. We can get the quenching rate constants here, the plots. And based on that, we can calculate the lifetime and also the efficiency is about 90%. This is one way to calculate the efficiency is see how much you quenched during this process. So the 90% efficiency for this one. We did the same excited state transient spectrum. And again, we see this bleach and the recovery and also see the bleach where rhodamine B, rose Bengal should be. And again, you can get these plots and this is what the triplet of rose Bengal is known. And that matches with the spectrum we have in the studies. So we conclude that we are transferring triplet energy. So that is the published rose Bengal, and this is from the last spectrum here. So it is long-lived. And now the question is how fast, right? In the singlet was very fast, few picoseconds it transferred, but it turns out we recorded the same thing and we took the slice from the this bleach recovery of the cesium-lead iodide and growth of this absorption. And you can see here that is the bleach recovery, but this one is growing. And you can see here, this is growing up to 1200 nanoseconds. And as compared to the singlet, right, this was the singlet when you did, see the time scales. By about 50 picoseconds, everything is over, but this is still transferring energy. So the thing here is the triplet energy transfer is slower than singlet. Probably because there is a flipping of spin is involved, right? So that is the one that you have for this one. Okay? So again, the take-home message from this one is the triplet energy is slower. So it is still continuing, right? So we wanted to do is go to still longer time scale to record how fast it is doing it. This is cesium-lead bromide. Now we are talking in nanoseconds. The previous one was, here it is about 1 nanoseconds. So now if you go further, you can see here it is still recovering. And it takes about, in this case, 2 to 4 nanoseconds to complete that energy transfer process. And we analyzed these ones and got the rate constants for energy transfer. And you can see here, they're all quite efficient in energy transfer, but you have these rate constants of the order of 10 raised to 9. So it is about 2 orders of magnitude slower than singlet. And that's why when you have cesium-lead bromide, we see only singlet because it outcompetes the triplet energy transfer. So this is too slow, right? So compared to this one. So these are the values for singlet energy transfer. This is triplet energy transfer. So we learned something out of this is this singlet and triplet energy transfer occurs with different kinetics. So what about in between? If we have, this was the bromide we had it, and this is the iodide I showed you. This is all singlet, this is all triplet. What happens if you have an intermediate band? So it turns out the kinetics is more intermediate, and it sort of tells us that there is both singlet and triplet are formed in the intermediate level. And again, we can analyze with this bi-exponential kinetics. That's a singlet energy transfer, and this is triplet energy transfer. And we can calculate what A1 and A2, that is the component of the fast, component of the slow. And using that, we can calculate how much singlet we are transferring. We are assuming that 100% here when it is bromide, and 100% triplet when it is this one. So if we assume that and try to fit with the bi-exponential fits, we get different both singlet and triplet. So indeed, these materials can transfer both singlet and triplet depending upon its band gap, depending upon the donor acceptor level. So again, this is something which we didn't know when we started. By doing all this series of experiments, we can now tell how this energy transfer occurs in the system. Okay, so again, if you plot the band gap versus the fraction of percent, here it is. That's a singlet and that's a triplet. Okay, so that is the reason here is much faster process. Although both are possible, we see only singlet. Here we see both singlet, the intermediate band gap in this region. And in this region, we don't see singlet, we see only triplet. So that is sort of a take-home message from the energy transfer studies, this one. So to summarize this first part, with cesium-lead bromide donor and rhodamine B acceptor, both singlet and triplet can be populated. Yet we observe only singlet energy transfer. With cesium-lead iodide donor and rhodamine B acceptor, only triplet can be populated. The lowered energy, this one. So there is a chemical review article. If anybody is more interested, there is also a couple of JAX papers on this one. So you can take a look at it. So it is an important process in the energy conversion, and we are doing it. Again, this is an ongoing research. Even the last data I presented, we have not published yet. So that is going to be soon. Okay, so that's the energy transfer, right? The same semiconductor nanocrystal can also transfer electrons. And how do you observe it? And one of the applications is, I mentioned yesterday, is in solar cells. Solar fuels. You may either water splitting to generate hydrogen or reducing carbon dioxide. And it's very difficult to probe the hydrogen reduction on the surface using spectroscopy because there is nothing spectral fingerprint. See, remember that we saw this rhodamine dyes fingerprint and we can follow that one. So in order to do that, we take this viologen compound. And this methyl viologen, when you reduce it, it can be very stable. It's a blue color dye. If you have any in the lab, take methyl viologen, put it in alcohol and degas it and hold before a UV lamp. It turns blue instantly. Alcohol reduces it. Okay. So, so that blue color we can see how the electron is transferred. And as I mentioned earlier, one of the things is we need to take away these holes. And if it is ethanol, that takes away the holes in this case. So that's what we are doing in this one. So the first we always try is to see whether it interacts with the semiconductor surface, and that one you can see here the quenching of the dye. Okay, you see here that it quenches, and that's you plot again this double reciprocal plot to calculate the apparent association constant, and it is quite high. So then the next thing is, does the surface matters? So we change the different surfaces here from oleolamine to olea, this one lead sulfate, DDAP, so all these things. And what we found is the association constant changes because it has to come and interact, right? So whatever there on the surface does matter. Then we wanted to look how fast the electron transfer occurs. And we recorded this transient spectra. And you can see here again, you see the kind of a familiar bleach. That is because disappearance of the excitonic band, and it recovers back in all cases. And now you add methyl viologen to it. What you see is there is a fast recovery in the first few picoseconds, and then it does not recover back at all. It just stays right there in all three cases. And the reason for that one here, so this is, we are plotting this change in the absorbance versus time, and here we have flipped the scale just to show you that here you see that initially there is a fast process followed by a stable process. And that comes from, again, we can analyze this fast process and get a rate constant for all these things. They are quite high. So the electron transfer is instantaneous to the molecule. But we still see this bleach, and the reason we explain is this viologen is bound to this nanocrystal, and the electron moves here, and the holes remain on the semiconductor, and as if you are extending the charge separation. They will eventually react back to this one, so but it's in the nanosecond time scale, it happens. So that is what we have. So here is the apparent association constant, electron transfer rate constant, how much charge separation you are achieving, and we are also measure the yield. So this one seems to be the best combination for all doing it. Okay, one of the things it happens is these were done in toluene solution. We wanted to do in more polar solvent. And one thing we found out was to protect the semiconductor nanocrystal was to give a polymer coating. And this is a typical process where we take cesium lead bromide, replace the oleolamine ligand with a monomer of this methacrylate monomer and shine light. And when you shine the light, you form this polymethyl methacrylate on the surface of the semiconductor. And that semiconductor is such, it wraps around and protects this process. So now this is cesium lead bromide in hexane, and this one with the PMMA. So it's very strong emission. And we checked for the polarity effect, it's still very emissive. Only you lost a little bit, but addition of up to 40% doesn't change much in the emission spectra. So it is stable, and we wanted to see what we can do with this viologen. So we excited with it, and we see very similar behavior. This is in the absence, and in the presence, this bleach remains. And again, as I mentioned, that the electron goes in here, the holes remain on this one. And here is, if you increase the viologen concentration, you start seeing this residual bleach more, and that is corresponding. You go to the 600 nanometers, you can see the rise corresponding to this reduction. So again, this is formed within 10 picosecond, and it does not decay in the time scale. But we went to the longer time scale, okay? Now in nanoseconds. Now we can see the recovery of this one and also decay of this methyl viologen radical. So how fast it disappears. So that is the back electron transfer. So you have transferred this electron in 10 picoseconds, but here it takes several nanoseconds to complete this process. But some of it can also escape and make room for the new ones to come in. Or the electron can hop out, right? So that gets stabilized outside in this one. And we wanted to look for that. And how did you look? You do a steady state photolysis. You take the same solution, hold before a lamp with a visible light excitation. Now you start seeing this viologen radical forming in the steady state. That's what you see in the normal process. And you can see here it is growing slowly. And then when you turn off, it comes back, right? So this is the back electron transfer on a longer time scale. So at this one is a steady state. I don't know how many of you have done steady state approximation. In a steady state, the rate of forward reaction and rate of back reaction remains equals, and that's how they get the same concentration. Okay? So that is the steady state. So based on this, we can calculate the back electron transfer, that's from this here, and we can calculate this forward electron transfer. That is the escaping from that shell I showed you earlier. So this one summarizes all the things I presented. So you have this complex here, you excite, within 10 picoseconds you form this bound cation radical. That one can back electron transfer with 10 raised to 7. This one, it can go, and some of them can escape and form these separate ones, and they can, this one. So this gives you in a nutshell, whenever you do a photocatalytic reaction, there are so many different steps involved. There is a forward electron transfer. The species that got reduced has to come out of the surface so that the back electron transfer is not there. So these are some of the key steps to keep in mind, whether you are making hydrogen or CO2 reduction or some other process. What you need to remember is what are the key processes that control this entire electron transfer process. So just to give an idea how we solve this puzzle by just using spectroscopy tools, all the way from picosecond time scale to seconds time scale. We monitored with different windows and were able to establish these different processes. So the ultimate net electron transfer was about 0.2 to 0.3. So although initially you may have transferred 100%, the 80% is lost, or 70 to 80% is lost in the back electron transfer. So that's why most of the time, whenever you do a photocatalytic reaction, the net efficiency is somewhere between 10 to 20%. Here it is little large because we also have ethanol in it. Okay, so that's sort of a summary of what I told you. We started with energy transfer and electron transfer. I'm sorry, a little more heavier in terms of experimental data, but this is sort of a current research that we are doing in our lab right now, trying to understand. So just to give an idea what it takes to understand a simple problem, we started with energy transfer and electron transfer in a photosynthetic system, and now it happens here. Okay, so that sort of concludes. So thank you.
Thank you, sir, for this colorful lecture on light energy conversion by unique metal halide peroxide. Second lecture will be start within a minute.
Hello. So, as compared to excitation and emission, Generally, we study that in excited energy is higher and emitted energy is lower.
Can you repeat that?
Excited energy is higher for luminescence.
I still didn't get it what you said. Excited energy?
Is higher
Yeah.
and energy obtained is lower.
Yeah, right. Yeah.
So it is a routine process.
Yeah, right. So it's a called downhill conversion.
Yes. But you shown you excited at 800 and observed energy is 610 nanometer. So generally we are
800, but-
expressing release of energy in the form of not only light but also via through various steps like
Yeah, yeah.
plate,
Yeah.
plate.
Yeah.
So these are the some energy losses we are considered in luminescence. So in case of 800 to 600, energy is up. So
No,
what
we, in this case, we didn't get 800, didn't get 600. That is the bleach, that the absorption of the dye went. We didn't see the emission. That is the phosphorescence. The phosphorescence should come out still in the lower energy. So it doesn't come in this one. So we should have seen, but we tried it, but we couldn't see any emission coming out. So what that 600 bleach you saw was the absorption. So the absorption, that means the dye got converted into something else.
bleaching process.
Yeah. So it is, we still a down conversion.
So here light of lesser light is of 400. Lesser light used for the
The first part,
is,
okay.
is visible light. Lesser 400 nanometer. Pump lesser 400.
These are absorbents. So this is not. See, this one is although around 580, that is the absorption of the dye. I'll show you where. Okay, so this is what the cesium lead iodide. That is the absorption of the dye. This is the emission of this guy, donor. So this cannot transfer singlet, but it can transfer triplet. So it cannot go to this state, but it can go to this state. And this is lower energy. See, this is where the phosphorescence should have seen it somewhere here, but we don't see it. So the triplet energy is much lower. So only in the singlet case, here we are exciting 400 and this emission comes at 560, 570.
Another thing is lesser pulse is of femtosecond
Yeah, this one is 35 femtoseconds. We have a laser.
in AFS.
Yeah, your car, right? So everyone carries, so nobody is bothered about it because we need it. So in this case, these are the experiments done to understand the processes. These are not intended for practical application. So why we use this one is that we can tune the band gap very easily. Whatever band gap you want by just adding, you make a bromide and add one crystal of potassium iodide and stir it. And the time of stirring will dictate how much you exchange you do it. So you can take out whatever time, because the potassium iodide crystal very sparingly soluble. So the exchange is very fast. So these are some of the properties allows us to do.
Perovskite efficiency is much more higher than others. So what
Yeah,
could be
because
reason?
these are highly
I think
luminescent.
we have reached 35% now.
The people have made up to 100% emission. But typically when you make it, you get 40-50% in the lab. But if you really control the surface, you can get up to 100%.
Maybe it is controlled entire energy is transferred.
Yeah.
So regarding energy transfer and electron transfer, so what will be the percentage of both?
So here, if you try to do it, what we have seen in the first study, about 70-75% is energy transfer and 30% is electron transfer, 25-30.
Okay, thank you.
Yeah.
So I have a doubt about the PL spectra, photoluminescence spectroscopy.
Okay.
Suppose we have the one material, any metal oxide.
Hold it.
Yeah, any metal oxide, and we have modified that metal oxide with any photoactive material. So at same excitation wavelength, there is a slight shift in the emission peaks after the modification. What factors can affect that shift?
Yeah, depending upon, the question was, when you take a molecule and bind to the surface, the emission peak is slightly shifted. Typically what happens is, when you bind to the surface, you are making a different species, because that binding is there, right? It is a charge transfer complex. So that attachment can influence its excited state. So that is a good indication that you are changing. Sometimes you can also see a shift in your absorption spectrum too. And if there is really a strong charge transfer band, you get a different band coming up. Like for example, if you had TiO2, some of these like catechols and other ones, they are earlier, you can get different colors.
But sir, that binder can affect the efficiency also. Binder can affect the efficiency.
Yeah. That's what I showed you. We had a different surfaces, and that can change the things. Yeah.
Hello, sir. Hello, sir. We have used two component system here. One is semiconductor particle, and other one is die. So the energies of the dies are fixed. So we say that HOMO and LUMO. And we are actually doing the engineering of the band energies of semiconductor with respect to modification of its surface by various components. So my question is that we are talking about the diffusional electron transfer. So in this, what we actually want to understand from this process is that when we say the electron transfer process, there must be some time lag of electron transfer between the donor and acceptor. So will it be possible to monitor that time lag using pulse spectroscopy?
Yeah, if there is a time lag, you can always should be able to see it. What happens is, whenever you see these changes, it's a collective effect. I showed you, like in the singlet and triplet energy transfer, when both were occurring, the kinetics was mixed. And we try to model it based on to separate out the two components. Same way, if there is an electron transfer and this one, you need to look for what is the different things and where is the gap coming. So it is possible to look into that.
Second, related to some modification, suppose that we prepare the electrode of this semiconductor particle. So based on the applied potential, we can switch the energy of semiconductor. So in that case, will it be possible to monitor the pulse spectra combining the two techniques rather than modifying the semiconductor?
Yeah, you have a good point. And we have done it in the past for not this system, but other systems where you can make it the semiconductor like tin oxide or TiO2, electron rich, and prevented electron transfer to the like dye sensitized thing. You can prevent the sin, and the applied potential dictates how fast electron can transfer.
The last one, sir. Suppose somebody wants to report the hydrogen evolution using semiconductor nanoparticles. What energetics we have to explain in the result and discussion part?
Okay, the question is, if a photocatalytic hydrogen generation, what parameters you need to consider? One is definitely the band energies, and most semiconductors can reduce hydrogen ions, so that should be okay. Other than your iron oxide, where it's much lower. But most of semiconductor, because conduction band allows it, so that part is okay. The other part is your light absorption, right? That is determined by band gap. And in photocatalysis, there are two parts. One is reduction and another is oxidation. And how do you control the one part affects the other part? So you need to tell, if you are using a sacrificial donor, you have to tell what sacrificial donor and how much it is contributing to the directly to the hydrogen generation. I will give an example, maybe I think tomorrow, I think one of the talks for this one.
Sir, last question. Actually, in semiconductors, we have seen that the majority charge carrier performing the major reaction and the minority charge carrier, say for example, N-type semiconductor, we are considering at valence band electron are more in number, so that reaction is treated as a major reaction, as a reduction reaction. And for a whole region, that is valence band region, if it is oxidation process, we are treating as a minor reaction. So in your all slides, what I have seen that we are everything considering about the conduction band to the linear of the die electron transfer process. So will it be monitored to have electron transfer occurs between die and semiconductor at valence band and the homo energy level of the die?
It can be done. If it is there, you will see it. But in this case, no, the valence band is not able to oxidize the die. This particular case, it is not. And another thing is also it's a competition reaction. So we have a little bit ethanol in it. So the ethanol is competing for the holes and it takes away. So that's why
We don't have to consider the minor reactions occurring in semiconductors.
Yeah, right.
Like say for example, in this we have to treat only the reduction processes which are more favorable in case of N-type semiconductor.
Yeah.
Okay, sir. Thank you.
Especially in case of semiconductor and sensitizers, usually, if you are going to consider about the connectivity, physical connectivity is one of the thing, and second is one can use linker moieties. So, especially for electron transfer or energy transfer, preferably the linkers are the best one. So, is there any criteria for choosing the linker, having the better transfer between both?
These cesium perovskite, they seems to carboxylic acid, amines, thiols, they tend to bind much strongly to the surface. And again, in this case, it was just a luck that the dyes we chose had a carboxylic acid, it's bound. For example, if you have a rubrine, it will not bind because it doesn't have any functional groups. But that's why we are studying them in the films. In the films, they have to come together.
Yeah.
So again, depending upon the situation, you can play around. The solution one is nice because you can do a lot of different techniques. Spectroscopy, you can use it with ease.
Definitely last. Sir, we are using the different delay time for the probe. So what is the selectivity criteria for selection of that 2 second, 4 nanosecond, 6 nanosecond delay time? Or is it randomly selected for?
No, we collect like 2,000
number of data.
2,000 spectra.
Okay.
The one you presented just to show you the incremental decrease. But you can set whatever
At
time.
the chosen interval, we can take
It's all
it.
programmed. So you say, okay, move every 10 femtoseconds or 10 picoseconds or whatever time you do it. What we do is in the first part, we collect more points because it's decaying very fast.
Yeah.
And the longer part, we just
That
spread it
steady
out.
part.
It- So I think another talk is there now, right? Yeah.
Thank you, sir. Second lecture will be start within couple of minutes.
So you had brought something there?
Get about this
Box. Okay, then forget it. Yeah. Okay, go ahead.
Sir, in photovoltaics, just we have to capture the electrons from the excited state. So, is it cause if the electrons transfer from excited singlet state to triplet state? Okay, so this process can affect the decreasing the efficiency of photovoltaics.
Yeah, it can. Because now you are losing the electron, right?
How to avoid this transfer from singlet to triplet state?
again, depending upon the molecules you choose. But that molecule can transfer electron to something else, right? So again, this is how you can build these assemblies. I showed you in one case.
Avengers.
One case very early on. So like here, this is transferring energy, but this is transferring electrons. So you can plan in such a way that it can be used for a benefit. But if you are just using only this energy transfer, then you cannot do anything.
So one more question, sir. So what is the relationship between the fluorescence intensity and electron recombination rate?
Fluorescence intensity, and that you have to get through the emission lifetime. Because it is a competition, right? So the fluorescence yield, even though if it is 100%, depending the lifetime could be 2 nanoseconds, right? There is a non-radiative decay is almost nil, but still it will have its own fingerprint. So when you have this radiative decay, so how fast it decays is independent of the fluorescence intensity. So it could be very fast and still be 100%, or it could be slow and still very low yield. So again, all these processes control.
So in this discussion, we are unable to understand, sir. Once we have adding the semiconductors in the dye molecules, so fluorescence intensity increases. Okay, so I am not getting electron hole.
The reason is you may be suppressing some of these processes, right? So if you can suppress any of these processes, your intensity goes up. So you need to identify which processes is affecting. These are non-radiative decay, so they don't contribute to your emission. These ones. So if you suppress that one, it goes up. Okay, so start with the next one. So what time is the tea time? 12. Okay, so we'll try to finish it. Again, I didn't delay this, okay? Okay, so the top part is gone, okay. Energy. Now I'm going to go back to trying to make solar cells, right? We talked about energy transfer, electron transfer. How can you convert them into electricity? How can you capture those electrons and make electricity? And there was a time period between, I would say, around 2005 until maybe about 10, 12-year window. Everyone was excited. This is before perovskites. This was everybody was trying to make quantum dots used for solar cells. And one of the advantages, you see that it's a tunable bandage. There were hot carriers. Hot carriers are this one is before they thermalize. If you can take it out on an electrode, you can get higher voltage. And they also talked about multiple carrier generation, although this is sort of a died out field in this one. So there are different ways you can make semiconductors. One is semiconductor heterojunction solar cells. You have a electron transport layer here, like zinc oxide, put a lead selenide, quantum dots on which you put a hole conductor and a gold contact, you make it. So it's as simple as that. Okay? Or you can, people also made polymer semiconductor hybrid cells, where they disperse these quantum dots in a polymer matrix. I think in the afternoon, Professor Patil is going to tell us more about organic solar cells. So this is sort of a hybrid between the two. And then we have these quantum dot solar cells. And the only difference here, instead of hole conductor, we have this thing. Okay, so I'm going to talk first about these liquid junction solar cells and something about this extremely thin absorber cell they call ETA, because doing it. Okay, so you know the synthesis of quantum dots, and you make it, and either you can drop cast. There are various ways of making films. Okay, you make the quantum dot by this hot injection method, and you can drop cast on a spin coater, it will deposit. The other one is you have like a mesoscopic oxide film, TiO2, tin oxide, zinc oxide, silica, all these things, they tend to adsorb, especially well when you have a functional groups. Like carboxylic acid binds to these TiO2, thiols, amines binds to the cat selenide. So that is at that time deposited films. You can also do what they call electrophoresis. Electrophoresis is not electrochemistry. Here you are applying an electric field and these particles move and get deposited on one of the electrodes. These particles are typically negatively charged and they go into the positive electrode and get stuck. Within a minute or two you can see it. You can even watch it how it moves. The cloud moves and then get deposited on this one. The other one, you can also use chemical bath deposition. Now this is a chemical bath deposition, is an old process. That's how all these your silver films and everything, they get coated. All these shiny things, the chromium plating on all your bumpers, car bumpers or shiny handles. You see, they're all chemical bath deposition. They have what they call there is enough energy there. So the moment it sees some kind of a surface, they get reduced or react on the surface. So you can do chemical bath deposition. Basically, you have a cadmium salt and sulfide salt, but they don't react to form cadmium sulfide, but under the right condition, it can deposit on the surface. But this one is the most interesting, is what they call Sylar. This is the most simplest way of making your quantum dots. You don't have to worry. You can go back to the lab and do it. Make a film of, say, TiO2 or a tin oxide on a glass slide and have two beakers, one with a cadmium salt, like cadmium perchlorate or cadmium iodide, whatever, and another one sodium sulfide, right? So you have got two reactants. So now what you do is, and have a couple of beakers to wash in between. So you immerse that one, and first you dip it in cadmium, leave it for 1 minute or two, take it out, wash it, put it into sulfide. So the cadmium ions, whatever that is adsorbed on the surface, now will react with sulfide or selenide to give you that cadmium sulfide or selenide. And you repeat this cycle again and again, and you can get, see the colors, same colors you see. So this is a simple way of getting your quantum dots on the surface, on your surface. And then you have to make a quantum dot solar cell, and you can put it here, and then you shine the light. So here you have optically transparent electrode. This is a solid state, this is a liquid junction. That is common. Then you put what you call electron transport layer, ETL. In this case, it is TiO2 or tin oxide. You can put it, that drives the electrons down, right? And then you put the active layer, that is your sensitizer, quantum dots. That is same thing. So this is what the difference is. In the liquid junction cell, the whole conductor is a redox couple. Here you put a solid whole conductor. And for a while this was a problem, and now there are several whole conductors have come, so you can put it. And now you make a top contact, and in this case it's a counter electrode, and your cell is ready. You want to play that YouTube? It tells you how to make a liquid junction. You can go with a faster speed. You can forward a little bit. Yeah, forward it. This is the electrophoretic deposition. Okay, sorry for running it fast because I didn't want to bore you, but you can go and watch it again, how to make a quantum dot solar cell. It's very easy to make it step by step. Again, for all the students, it's not only doing experiments in their lab, try to be creative, make some videos, post it in the YouTube, whatever you are doing, okay? So it helps others, it promotes your own ability to communicate. So it's always a plus. So all of our students, if you see the kamatlab.com, we have a multimedia, we have a lot of videos. And again, these are all students done. I just sometimes tell them, okay, why don't you consider doing it? And they just, some serious, they do it. Again, there is no pressure on that. Their own liking, they do it and enjoy it. Okay, so this is the chart. So now you are exciting these ones. You are driving electrons to this electron transport layer to the conducting glass electrode, and here you have a whole conductor trying to do it. So that's what we do it, and this is what that Sylar method was. You can dip it, wash it, selenium, dip it, and you can get this same process. Again, it's very easy to make. And what we had one paper was, does it make a difference what you start up with, whether first selenium or first cadmium? Just thought came in. And this is what we made two, one with starting from selenium to CD and CD to selenium. And you can see here the growth process was slightly different. Doing with the selenium first, and then CD was much little slower. And then we compared, I think, the photo performance. Nearly identical first 5 cycles. Later on, it changes a little bit. And again, we use these TiO2 nanotubes. And you can see here, they are getting deposited on the top of it. Again, you can see here how they cover these particles with small particles, these tubes. This was, again, done a while back when the field was very hot. The other one we tried was with these bifunctional linkers, where you have this mercaptopropionic acid, and when you add it, you can get amines replaced, and this was another one that you have. And from that, you can get the absorption spectra, and this solution and film, they show very similar behavior, and we made the quantum dot solar cell. And you can see here, this is different size particles attached to the TiO2. And one thing that struck was these efficiencies at these excitonic peaks. They were increasing with decreasing particle size. And the reason we thought was the smaller size particle has a larger band gap and has a more driving force. And that's why you are seeing a better one. So that was the argument made at that time. Later on, even we measured these electron transfers, and indeed it was to be true. And here is an example of what we got. At that time, we got 5.4%. we were so excited to get 5%, okay, at that time. So again, see here, we published in JAX 2012, manganese doped quantum dot sensor, it's 5%. We could have gotten. Today, if you make even 15%, you will not be able to publish in JAX, okay? So how the time changes, because these are all learning process. We are trying to make it better, and we show it's very steady and happening at the time. Again, earlier there was a question about lead, cadmium, it all comes, right? Can we design with safer within? 150-year-old lead isotope still dictates the operation of a modern automobile. Doesn't matter what kind of electronics you have, that battery sitting there is a 150-year-old technology. Nobody has replaced that. Okay, so one of the things, these new semiconductors are coming. So you can use these semiconductors. You don't have to use cadmium, right? So there are a variety of these ones, and many of them are not being studied well. So here is an opportunity. If anybody wants to get into this area, here are some compounds you can try. And they themselves say a lot of things. When you change the ratio of copper to indium, the properties change. So this is another one. They also show size-dependent properties like any other. So this is the diameter of the particle and the band gap. So you can, for example, copper gallium sulfide, you can change from 4 to about 3 once, whereas copper indium sulfide from 3 to you can 1.5. You can cover the entire visible region. So this is another one. So we use copper indium sulfide for that, and they make these particles of different sizes. And you can see here there is a quantization effect. It doesn't show excitonic peak as prominently. There is a lot of this tail absorption, and that is mainly coming from these intraband states. That's responsible for it. As a result, the absorption is, emission is also very broad. You can see here it goes all the way down. And again, we made these solar cells of different diameters and doing it, and we found out that this is the efficiency or IPC, people call it, for every 100 photons, how many electrons you can get. We got about 40% in this case. Typically, it should go about 80 to 90%. But this was just to show that this can be made at that time. And the later one, the certified efficiency was 11.6% with these kind of systems. So there is still room to improve these kind of materials, but not many groups are working on it, so that's a good thing. You can jump in and show that you can do better than others doing it. I think, okay, addressing the issues of sulfide, polysulfide couple. So one of the problem is redox couple. When you use sulfur, your counter electrode cannot be like platinum because it poisons the surface and a very sluggish electron transfer. So we were looking at that time for a new one, and what we found out was copper sulfide can mediate whole transfer. So even, for example, you can get Cad sulfide. So the copper sulfide is a good whole transport material. And so we use this one to do it. People used to use brass electrodes in this as a counter electrode, but the problem with the brass is if you put in sulfide, it dissolves after a while. For a short term, it gives you high current, but it's not stable. So what we came up with is different strategy where you use this graphene oxide, you add copper 1+. This is a magic reaction. So use sonic rate washing reduction, the copper gets bound to the surface and gets reduced. And everything starts precipitating down at the bottom of your flask. And and we take that one and expose it to sulfide, and either you can directly deposit on a carbon paper, so that's sort of a thing it looks like when you deposit on a carbon paper, or you can also use a binder like polyvinylidene fluoride and make a paste and keep it, and that paste is a counter electrode. You can put it on any electrode and work fantastic. So if you have platinum, your same electrode, you get curve like this. If you just use without binder, that's your JV curve. And this is what you get with a binder, very nice JV curve. And so you can see here now that 40% is now about 80%. So that counter electrode problem we solved at the time. Again, you can see here it is old work, but it's still good today. So it looks like a small thing, but everyone then started following this procedure, and it works great for counter electrode. Again, I'll skip this one. Okay, this is that energy transfer I was talking about, where we showed that we can do the energy transfer spectra. So that's the paper. So this is another way to change the band gap, is changing selenium and sulfur ratio. And we wanted to see whether we can put all these dyes into this thing. And the idea here is the smaller, more sulfur has a larger band gap, and selenium is smaller band gap. So the idea is when you excite all these things, they will come here, either energy transfer, electron transfer, they all get excited here, and that way we can drive the force. And here it is, this was done, absorption spectra and emission spectra of different ratios of selenium and sulfur. So you can tune the entire band gap between sulfur and selenium by just changing the ratio of sulfur and selenium. And interestingly, they were all, we picked the same size particles. The size was same, it's only the anion was different in this case. And you can see the glow here of different particles. So now we wanted to see whether we can sort of a tandem design, we want to make it. We use this electrophoretic deposition. So we apply electric field, the particles go and deposit, and we can follow the absorption and how it is growing at different times. And the interesting part is either we can do selectively layer by layer, or you can mix all three, right? So basically you put the first, this having more selenium, that is smaller band gap all the way up front, right? So we want to get this band structure here, this band structure. So we put this red dot or the green dot first in here, and so we can control what we do sequentially. And when you do it individually, that's how it looks like, green, orange, red. We call it, that's the green, orange, red. And this is increasing selenium to sulfur ratio. So more selenium here, more sulfur here. And you can see here it responds to the same kind of a behavior of the absorption. And again, as expected, this absorbs less, you have a less current. This absorbs more, higher current. But what happens if you combine the two or three? What we saw was a higher efficiency when you combine these three in a sequential order than a mixed order. And again, it was a proof of concept. It is not something that you can write home saying that we made a big discovery. So we wanted to see this kind of a putting together different semiconductor quantum dots can enhance the efficiency at the time. So this was a conceptual demonstration, and again, it worked fine for that one. Okay, so that's the idea that why it is working this one. So another thing, I will just be very brief on this. So from that one, we moved to the solid state. And the student started at the time, Jeff Christians was very well involved. So we never made any solid state at that time. So he adventured in, again, this is your FTO, you have a mesoscopic TiO2 film on which we deposited this antimony sulfide, then a whole transport layer, and this one. And the idea here is we wanted to probe all the processes, and that's the efficiency we got. Again, very low efficiency, right? But at that time, you could still publish it as a major advance doing it because very few people working. We looked into, again, the transient absorption spectroscopy. Again, that gives you an idea about these holes getting accumulated in this one. Again, we studied the whole transfer process in this one, and I'm going to skip this because the idea here is when you have a hole conductor, right? So it is not only, this is an active layer, but the whole transport within this one is also a limitation. That was we wanted to show when you transfer a hole to a hole transport layer, it has to diffuse to the collecting electron. The thickness of this one matters. So both your extraction of electrons and holes need to be taken out at the same rate. Then only your solar cell is more efficient. So I'm going to skip this. Again, we did the thickness dependent on this rate of hole transfer, and it was published earlier. Okay, from there you got dye-sensitized solar cell. Remember, we went to quantum dot solar cells. That's the extreme thin absorber cell. And finally, we got the perovskite. So the beauty of science is, even when you are getting a negative result, even when you're getting a poor result, you always learn from it. There is a lot of learning process in these systems. Although the efficiency from today's standards, they look uninteresting, there is very good science went into it. Because of this knowledge, they could make efficient perovskite solar cell. It didn't take much time to make them. So that is where we stand today. And this is, if you go to the current thin film solar cells, those are the efficiencies we have. These are the champion efficiencies. Remember, I used to show like 3, 4, 5, 6, 7%. Those are all history, right? These are what now the champion cells. And we'll talk about it more when we do the perovskite later on. Okay, so what I showed you was a simple way of designing a quantum dot solar cell. If you want to study, again, when you are showing, if your focus is on scientific understanding, don't focus on the paper efficiency. Nobody cares. But when you say, I made a highly efficient cell, and you claim only 10%, somebody's going to tell it is not highly efficient. People have made it whatever percentage we saw it here, right? But you say, well, I am making this cell not from an efficiency perspective. I want to understand how does the whole transport occur, how does the electron transport occurs. That's a scientific understanding. So again, what you focus in your research matters when you write a paper. Thank you very much.
Thank you very much, sir.
See, I still made it in the coffee time. Okay, sorry. Thank you.
If anyone have question, please ask.
Yeah.
Some cases they report IPC values which are more than 100%. So getting more than 100%
You know,
for IPC
measuring IPCE is a very tricky thing. Okay. The reason is your calibration, because it's always calibrated against typically a silicon solar cell. And if that calibration is off, you will get different one. So the careful workers, they calibrate often to, basically you take an IPCE of your silicon solar cell and see how it looks, right? So, so that calibration curve can offset. It cannot go more than 90% because there is also a reflective aspect is there. So 90%, if you get it, that's the champion.
So, but in papers they write there is some double exciton or something which goes
You can
beyond
make up
90%.
any story you want. Okay? I'm just saying that's what people are making up. They don't say, that's where the artifacts are, right? If your calibration is screwed up, you can get a whatever value you want. You tell me what value you want, I will get you. It's IPC, for those of you knowing, IPC is number of photons, number of electrons generated, which is reflective of the photocurrent, divided by the number of photons incident. And typically it should be 100%, ideally. That's the maximum limit. For every 100 photons, you got 100 electrons. But people get it around 90-ish because there is some reflections from the surfaces and occurs when the photons incident. And how do you measure is, it's you can easily measure number of electrons, but number of photons measurement is very difficult. So what they do is they take a reference cell silicon, and the company gives you a calibration curve. Okay, nobody checks it. So you take that calibration curve and use it to normalize your values against that calibration curve. And often it happens is your calibration cell setting may not be right. Okay, it will give you a little lower intensity, but still it gets normalized to the right intensity. So then suddenly your denominator is lower, so you get a higher efficiency. So anytime you violate these ones, there is, I don't want to say that, but there is a lot of in plasmon catalysis, all these plasmons. People are omitting the heat effect. Most of the time it is the heat effect. It has nothing to do with plasmon. Yes, the plasmon absorbs, but it generates heat. Then they will say hot electron transfer, hot hole transfer, all kinds of stuff. So you can make up whatever explanation that fits your thing whenever you make these high ones. But it's extremely difficult to get an IPCE more than 100%. I can tell you there is a paper for, I think it is hydrogen. I will give you an example tomorrow. Remind me. In that one of the afternoon thing, the people reporting in Nature Energy more than 100% and claiming it to be a multiple exciton generation. That's a wrong paper.
Sir, on similar lines, if we talk about APC or the internal quantum efficiency.
Yeah, APC is absorbed photon conversion efficiency. If your absorption is significant, you can get a good value. What people do is when the absorbance is like less than 0.1, they try to get APCE. That's very difficult. Again, there is error prone because when you have like 0.04 absorbance, because people sometimes put on the electrode some molecules, which is very little, and they want to show you the efficiency numbers high, and they come up. But it is very susceptible for error in calculation. Whereas if your absorbance is high, like 0.4, 0.5, then easy to calculate absorbed light.
One of the method you mentioned that Scylla method.
Yeah. It was very popular.
Scylla is popular, but what about stability?
Very stable. Those are quite stable, like any other ones.
As compared to vacuum.
Again, like any other things, it will degrade eventually. But if you want to make a cell and use it for a month, it's fine.
So, by using vacuum, thickness and uniformity can be maintained.
Yeah. Again,
What about Scylla?
Scylla, again, I showed you, you can get whatever the quantum dots you want, right? What?
It is like sulfur selenium.
Yeah.
So there is a possibility of sulfur is much more harder than Fe.
Yeah, again, these are all experiments were done to show the proof of concept of these things. Not to make any commercial cells or anything. Just to understand, the thought comes to your mind, what happens if you have different size particles stacked together? We used to call it the rainbow solar cell, which is not, it's actually become black, but still different size particles, if we can put together, can we get a higher efficiency? That was sort of a thing it started with, and that's how we did. But the cadmium sulfide and selenide are much more stable than the perovskites.
Basically, it will be adhered by chemical or absorption is very chemical absorption or physical absorption?
Again, it starts to build. Initially, it binds to the surface, and then over that, it starts growing. Yeah. Yeah. You can also use electrophoresis. That's the easy one. Yeah, we have tried all these different methods. Again, depending upon the experiment we are doing, we use different methods. But that's all history now. Nobody talks about Sylar or anything. But it's a beautiful science. We really enjoyed it, working with it. So that is one thing. You know, when you work for a long time, there are so many phases in your research. You get excited, you think, but then the next new thing comes, you forget about it, right? So you go to the next one and next one. So that's the fun of being in the research. You have to find a new way to get yourself excited doing this research. And it gives what? Yeah, you can still work on it if you have something to problem. Yeah.
Shed some light on measurement of IPC for PVC cells.
Yeah, PVC cells also you can do it, but the problem is you have to have a monochromatic light and you have to measure the yield of your product. Some people do it. Nowadays, because you got diode lasers, you know, the small lasers like your laser pointer type, you can buy commercially, and then you can do it. Because if you do the monochromatic light, your intensity goes down. So here with the, you can buy this about 10 different wavelengths and then excite it controlled intensity and then measure the product. And then you can generate your own thing because you know how many photons you are putting. The other one people do is what they call actinometry. And that's what we have been doing it. There is a ferrioxalate actinometry, which is very common. So you make ferric oxalate. So if you want, I can send you how to make it. And it's a ferrioxalate solution, ferric. I think when you shine the light, you convert into, I forgot, it's ferrous to ferric. It forms. And it is very quantitative. And there is a table that tells you for every wavelength what is the quantum yield for that one. So just like your IPC, you run that experiment under light. So if you are doing experiment for 20 minutes, you run it for 20 minutes, same light conditions, measure the conversion of ferric, and then you run your experiment, measure the yield, and the ratio of the two gives you the actual quantum efficiency. Yeah, look for actinometry, ferrioxalate actinometry.
Regarding perovskite solar cell.
Which one?
Perovskite solar.
Yeah.
Efficiency at minimum group efficiency higher than 30%. Almost most of the research groups are reporting around 25%, 30 like that. So what about the commercial feasibility of perovskite solar cell? Because
So we'll talk about tomorrow. Tomorrow or today, I don't know when it's scheduled. Today talking, tomorrow. Tomorrow, okay. So he was talking about in the lab, people are making efficiencies. And those efficiencies, you have to take out a little more carefully. So this is what most of the scientific literature now comes, is everyone wants to hype, right? So they think that by putting a higher efficiency, they can get a Nature Science paper. And there is an NREL chart recently, the efficiency moved from 26 to 26.1. And we recently wrote an editorial analyzing all these values. And it turns out the higher efficiency went from 26 to 26.1, came from decreasing the size of your area cell from 0.1 to 0.05. All other parameters are same. So just like your IPCE, if you do a small error in your area measurement, that 0.1 can higher if the area is slightly less. And they should not have entered that into the picture, this one, in the chart, but they did. And so basically, typically they use 1 centimeter square %, and the 1 centimeter square is still 24.1%, not 26. So that's where this one. All the commercial large panels, the efficiency drops. They are about 18% when you go to large panels. So again, these are all gaming the numbers, how to get higher number. And that's why people get excited and they go to the higher IPC number and then make up a story and get published. So this is, but if you read carefully, you can find out the problems in the paper. And often it gets ignored. So just don't trust because it's published in Nature Energy or Nature or Science. These papers have problems. Try to analyze. We try to do it. If somebody presents it, we rip it apart. What things wrong or what are right. Some of them are very good. We enjoy it. But some of them are not. See, right on time for tea.
Ladies and gentlemen, now it's time to take a short break and recharge with some tea. When we convey, we'll have the pleasure of listening to further lectures. Please be sure to return promptly in 15 minutes. Thank you. Enjoy your tea.
Hey, is the next one is ChatGPT? Next one is ChatGPT, right?
I hope you had a refreshing break and enjoy your tea.
I'm going to stand up. Should I start?
It's now time to resume our lecture and continue with our third lecture for the day. Ladies and gentlemen, we are delighted to have Professor P.V. Kamath sir with us once again to share their expertise on the topic of how ChatGPT and other AI tools are making a change in scientific publishing.
Okay, I hope you had a nice tea, and this talk will be, I think, much lighter. Again, this is something coming up. Yesterday I mentioned that everything is changes, right? Whatever that is valid 10 years back, it didn't. We used to type manuscripts. You now send it through the cloud and internet, everything. So same way, last November, there was a thing called ChatGPT came into play, and everybody started exploring. And there are a lot of concerns for scientific publishing. Before I start, I want to say I'm neither endorsing it nor I'm saying should not use it. There are pros, there are cons. There are things that you can use it for making your writing or publication good. There is also, it's an easy way to screw up and get into trouble. Okay? So you can write your entire PhD thesis with ChatGPT. And if you do, if not today, tomorrow somebody will point it out and it will be withdrawn. So again, be careful how you use it. So the purpose of this talk is to do it. How many of people have used ChatGPT? Okay, here using it. Nobody use it there? Come on. Okay, even if you go into your Microsoft Edge, there is a sign B there. That is the Bing. That will give you the whatever you want. Okay, so let's start. Again, on my own, the project does not endorsement or condemn GPT. Here are for discussion purpose only. Please use your discretion, okay? So you are responsible for whatever you are using. Don't tell tomorrow that I sort of told you to use it. No, don't do that. It's your responsibility. You are using it. Okay. So again, there are a lot of articles have come and doing it. Like for example, in January, we got from our faculty honor code officers saying that they have formed a committee and they are to recommendation. And also they said at the end of last semester, some undergraduates are already using ChatGPT in their final exams, right? So this is a concern for the university. So everybody is doing it. And then alarmed by AI chatbots, universities start revamping how they teach. This is a New York Times article. Then again, later on, around 18, there is some guidance came in. They told all the faculty to try to familiarize yourself with the technology. You better know it before students know more than you, right? So we recommend that you try entering your assignments into ChatGPT so you can see what kind of results you get. Right? So you can just put in assignments. So sometimes it gives you right, sometimes it's wrong answer. When you give an assignment, talk to students about whether using and other web tools is permitted. The implication of technology will vary by discipline. This is just to give an example how suddenly it sort of poured in and everybody woke up and trying to see what to do, right? Okay. There are a lot of cartoon series. This is gone now. Tina, I no longer need a technical writer because AI can do all that nonsense. Okay, did you just fire me while I was diminishing my contributions? Okay, here is an example of a conversation I will never need to have with it, right? So this is the reality. So AI cannot just bounce you back on what you're trying to do. How many of you use DALL-E? Please use. DALL-E is great for making your TOC graphics, okay? Also, you can try it. It's excellent. So here is an example. You just write, I need a solution in a test tube held in a hand with a green glow under blue light on a lab bench. It can produce this one. You can say, I want a monkey on a tree holding an ice cream cone, wearing a hat, sitting on the beach. There you go, right? It can produce it. So you don't, you can, and you can modify it, okay? So this is what we had a TOC graphic. This is not DALL-E graphics, right? One of my graduate student, we wrote on a called Sun Believable Solar Paint, and we wanted a sun to be having a paint and a brush. So he took maybe a day or two to draw this figure. I wanted to see something similar can be done. I said sun with dark glasses, holding paint bucket in one hand and brush in the other. So there you go. Okay, so again it created, I said, give me some more variations of this one. So there is different variations. So you can keep on doing more variations, you can do it. It's very convenient to do these kind of things. And this is the one, I said, I was writing an editorial on one of these mastering the art of scientific publication. I needed a TOC graphics, okay? So I said, a robot writing an article with a pen and a paper sitting across a table with coffee cup. You just type whatever you want, right? So it generated these 4 things. So I sort of like this one. Okay. Then I said a robot writing the same thing in watercolor and pencil style. So it created in a pencil style, and I think I picked up this one and it got published. It is perfectly fine to publish, but you have to indicate that this picture was drawn from DALL-E too. Okay? You acknowledge the source where you got that figure from. So that's what I did, and it got published, no problem. So if you are using it, make sure you acknowledge that it was done by it. Okay, you can revise the text. So this was, for example, just to give an example. So I was giving a talk on ChatGPT, and I wrote this one. And I said, revise my abstract. It revised my abstract. It is a fantastic grammar tool. Okay, so you can see it, how sort of this one. So it is hope that this presentation will spark a productive conversation. I didn't say that. Hopefully this short presentation will lead to a productive discussion. It changes the sentence, but keeps the same meaning. So you have to watch out when you're asked to revise something, whether it is done it right. Okay, so that is one of the things. It can create statements. Again, this is one of the worry. Like, for example, students, when you write personal statement, right? You can ask ChatGPT, feed it whatever your CV, it can create it. But make sure you read it properly. Edit it properly. So this is, for example, our university is coming. This says, I asked ChatGPT to write 300-word strategic plan for a major research university. It took 10 seconds. Right? So these are the kind of a thing. Research. We will invest in the recruitment and retention of top-tier faculty and students. Teaching. We will strive to provide the highest quality education. These are the kind of things you see in the brochure. So it can create. This one, again, somebody else tweeted this, faculty hiring committees, when evaluating diversity statements. So in the US, it's one of the common thing. Again, it says like a personal statement. As an academic, I'm deeply committed to promoting diversity and inclusion in my field and in the broader academic community. So you can create anything you want, right? So these are the things. You can also search for methods and protocols for anything. If it is in the database, it will give you. So for example, here, how to fabricate perovskite solar cells, numbered bullets, bold. Right? So it gives you preparation, precursor solution, coating, drying, annealing, deposition, all these things. But it forgot one thing, not accurate. It missed the whole transport layer. So it is not 100% accurate. It tells in confidence. I will show more examples. One of the things people have found it used to writing Python codes. That is been used. And you can see a general knowledge of how programming script works. There are better tools than ChatGPT to learn Python and programming, but how do I write a Python script? You start from the beginning. You can always tell me in terms of convincing a 5th grade student. So it will give you very low level explanation. So again, open a text editor of your choice, Notepad, write the Python code in the editor and save the file with extension. To run the script, open a terminal on command, navigate the directory where the script saved, and type on the script name. Here is simple example. So again, it gives you, can you give me resources to learn Python? It will give you. It can sort of write a Python script for the parameters of a quadratic equation. So it writes you all these things. But what if I want a complex number? No problem. It can create. So there is a lot of good things. Okay. So you need to explore the right things. Write working codes for simple problems. Clean up your code. Help build parts for complex code. Save a lot of time when you don't know what you are doing. Okay, this one, it started last December when this Ahmad Kirwani, he's in University of Victoria. So he wrote a lot of poems, one on batteries, one on solar cells. It will write beautifully, okay? So you can see here, batteries, oh batteries, powering our device and toys, in our phones, laptops, cars, you are the source of joys. Small and powerful, it's so discreet. Oh so bright, harnessing the sun powerful light. So it makes it very nice. You can also ask her to some other song, right? Whatever singer songs or popular song, it will write in that thing. Scientific humor, they are not that great. Okay, this is on writing on ACS energy letters, the journal. It says they don't make good jokes. And then this is Cranford, he wrote on a song on a rejection letters. So again, a lot of people have fun with these kind of things. I asked to write on a Shivaji University. Okay, so this is on Shivaji University. It says that in the heart of Kolhapur's expanse, I didn't say Kolhapur word, okay? I say Shivaji University, Maharashtra, India. Where history and knowledge danced, stands Shivaji University, proud and grand, a beacon of learning in India's land. Majestic, okay, goes and then it says, nurtured by Maratha's mighty grace. It's place where cultures embrace. See, it makes a nice. So if you want to impress somebody, and your friend, your fiance, or whoever it is, ask to write a nice thing. Give something what you want to say. It will write a nice poem. Okay. So next Valentine's Day, you can send that to person. Okay. There is also, this is what now is being used. Okay, that tells you how it's changing. There are two articles have come, one in JAX and one in Angawante by the same Omar Yagi. He does a lot of MOPS work and he collects a lot of papers. And this is not in ChatGPT, he used some other AI tools. And then you can just give the links of the PDF files to that AI. It will go through your paper and summarize whatever data you want. Okay, if you want synthesis, it will tabulate all different syntheses people have used. So this can save a lot of time. Rather than going through, like, if you have 100 papers and somebody was telling that they want to work on AI, machine learning, you need a lot of data. So this could be a good source to identify what to do, and that's what they do. So they have these PDF files. So this is a human pre-selection and AI-assisted coding, text segments, embedding search, and filter text segments. So again, either way you get this paragraph classification, how they do synthetic paragraph, ChatGPT with chem prompt, and tabulate the data. See, you have got, again, you can go and read those papers, see how they are doing it, and there may be more to it. Okay, again, when concerns came in, there is a guy in Bruno Erler contacted me and I asked him to write a thing. And he wrote a nice article, how it's going to change the scientific publish fundamentally. In the past year, multiple AI systems have showcased production of visual and textual content increasingly indistinguishable from human-generated work, creating almost overnight new possibilities for intellectual workers and at the same time raising potent concerns. We'll see what concerns now, right? But he also prompted, if you go to this paper and do it, can you just click on this one? He wrote a perspective article on this one by just asking questions to the ChatGPT. Okay, just asking. So it writes a paragraph. It looks like things. Okay, go up. Yeah, this is the article. Okay, go up slowly. Go up. Yeah, that's the abstract. It is written. Go all the way in the middle, about page 19. So this is what the final manuscript, but he tells you how to halfway. Yeah, slow down. Oh yeah, right here. So here, what it is the orange one is human added text. All question prompts are in green. And this is the one he added the title and written by this one. And he says, write an abstract for the following article. And he copied the main text. It wrote an abstract. Go up. He says, introduction, explain in detail why lead halide perovskites are promising material for optoelectronic applications. It wrote this one. Okay, go further down. So, however, these materials contain lead. Tell us why lead is important for them. It explains. Again, he added some correction. Explain lead toxicity. Okay, so, okay, now change. So, basically, you can write the whole thing, just asking questions, right? Of course, this was not a published paper. This is just in the supporting information as an example how things are done. Okay, so that is the one I showed you. Can AI write a scientific paper? You ask the question to the AI. And he says, AI can write a scientific paper very confidently. In fact, there are already AI systems that can write scientific papers. And this allows AI to quickly and efficiently generate. But it also says, however, it's important to note that these AI are typically not original research, but based on the existing research. Whatever there in the database, you do it. If you feed a PDF file, it goes into the database. So it is also a two-way street. It's not just a one-way street that it gives you. It also takes information from you. So you have to watch out what you feed in. And other tools. This is recently came in, how ChatGPT could disrupt scientific publishing. And this is a concern. Many editors are concerned that generate AI could be used, easily produce fake but convincing articles. Companies that create and sell manuscripts. There are a lot of companies, including in India. Okay, that's when they give you free degrees and all kinds of stuff. Authorship positions to researchers who want to boost their publishing output, known as paper mills, could stand profit. Most of the early worries over LLMs in peer review. That's another thing. So a lot of now platforms say no reviews for this one. And here is their survey. They found that it helps researchers without English as a first language. It's a grammar tool. Just like when you're writing, it can suggest you corrections. If you do a spelling mistakes, it tells you. Same way you can use ChatGPT to correct your grammar. Okay? Make coding easier. That is next one. Summarizes other research to save time reading it. So that goes down. So this one is the worry, and that's the future is the red one. Okay, now I told you some of the things that what you can do, and AI-driven language bot can help to break mental log jams when writing or when struggling to write those first words. Be used effectively to improve the title, abstract, conclusion of your manuscript. Provide a structure for writing by breaking up difficult topic into smaller pieces. Level the playing field with regard to non-native English speakers. In future, this language bot and others will almost certainly be included directly in other interfaces. Again, Microsoft Office already probably this one. Provide knowledge in the area. The Microsoft Office gives, for example, in the University of Notre Dame, they have blocked it because they don't want students to use while writing Word doing it. If I try to get into the Microsoft, it warns me that I cannot download because my email address is affiliated to it. So some of the universities are blocking the use of it. Otherwise, it is built in. If you have a private Microsoft Word, you can download it. You can get it. Provide knowledge in an area which has digest. These ones. Again, so far whatever I told you is some of the good things, right? You can use it. This is what are some things that we need to be aware of. What it gives you false things. Your status report appears to have been written by a commercial grade AI. Thank you, I appreciate the compliment. Add some mistakes so it looks like a human did it. So you can take a ChatGPT output and deliberately introduce some errors, right? So it looks like a human. Okay. Here it is. Can ChatGPT be co-author? People have published a paper with ChatGPT. Okay, so the answer is no. You cannot. You cannot submit because whenever you publish a paper, the co-authors take a responsibility, right? They are responsible for, and here nobody can take a responsibility. Again, there is articles written, scientists, please don't let chatbots float up to co-authors. Again, it's a useful tool, but not a person. So provide a completely reliable, 100% accurate. Do not mislead public into thinking can do it. There was a tweet, somebody said, friends don't let friends co-author with ChatGPT. Listed as author on research papers, many scientists disapprove. So a lot of discussion went on to it, but now this. So abstract written by ChatGPT fool scientists. Okay, like a lot of predatory meetings and other things. People, you can write on anything and doing it. So these were 50 medical research abstracts. That's again published in JAMA, New England, all these things. Okay, so I will tell you one more thing. As an editor, we always want to be a step ahead. So I wanted to see how it will write a review. So I picked up a title, just arbitrary title, right? And it says write a review. It says write a 3-paragraph review for the scientific article title, enabling just the title, nothing else. It wrote a review just based on the title. Here. It notes oxygen evolution reaction, it knows as OER, right? And the authors of the article have developed it. This one goes into detail. How did it know that it went in detail? I just gave the title. That's what it is. It just so confident it can write. Used to create electrocatalysts additionally. Overall, the article presents a well-conducted study that makes an important contribution to the field of electrocatalysis. He didn't even read the paper. It wrote that fake review, right? Okay, so I said, okay, can you write a negative review instead? The same ChatGPT said it is the greatest work. Now it is trashing the work. Firstly, the authors do not provide enough experiment details and data to support their claims, right? Furthermore, the writing of the article is quite technical and dense, make it difficult non-expert to understand. How did it know? I didn't even give the article. It says, in conclusion, oxide catalyst has some promising ideas, but the lack of experimental data, complexity, and the study lacks depth and potential. These are some of the things you always read it, right? So it must have been in database. So it filled it up and used it to produce this one. Okay. Okay, I said based on the reviews and rebuttal, can you write a decision letter? No, sorry. Can you write a rebuttal letter to the editor? Because you're assuming that the editor sent you back the comments and you want to respond back the positive. And the dear editor, see, it's always your name. It also gives you the thing. We appreciate the time and effort taken to review our article enabling this one. In regard to the experimental data, we would like to clarify that our study was focused on the synthesis and characterization and not on providing comprehensive things. And regarding the complexity of the writing, we apologize if some parts of the article were difficult to understand. We'll make sure the manuscript will make more accessible. So it wrote a rebuttal. Now we say, okay, write a decision letter. Based on a rebuttal, can you write a decision letter? So whenever you don't give any prompt, it always gives you positive. So in this case, it decided to accept the paper. Okay. So, okay, based on this one, after careful reviews, we have decided to accept your article. And we would like to request that you address the following thing. It added this one. It must be there in the database somewhere. Please submit the revised manuscript within a month. It created a decision letter, right? And then I said, okay, could you please write a negative decision letter? It writes a negative decision letter. It says we appreciate interest, but we encourage address issues. So this is the story of ChatGPT. It doesn't have an analyzing brain. It gives you whatever information you want without even checking, right? So, and then the dangers of using models for peer review. The real risk here is that LLM, again, this is from an editorial in Lancet, that looks properly balanced but has no specific critical content about the manuscript. If you look into that one, the comments were all general sentences. They didn't point out the specific thing, anything. So that is one of the things. So if somebody is using it, you can always, if you get a review like that, you can point out that it looks like it is an AI generated one. Because it summarized the paper and methodology remarkably well, it could easily be mistaken for an actual review report. It can summarize. If you give it something, it can summarize the data. Even worse, the specific but unrelated comments could be perceived as a reason for rejection. It's important that all participants within the peer review process remain vigilant. Again, people are given like MBA questions and they say they can pass through, take points of, some of them are good, some of them are not. Okay, there are a lot of in this kind of blog posts coming up, the efficacy of ChatGPT. Is it time for librarians to go home? Right? If you are there, why do you need them? So they apparently checked 29 citations. Only one was accurate. Any citations ChatGPT gives is always wrong. It is so confident. And there was another thing, I think it is, the system did give a shout out to library noting that it is also recommended to consult librarians. Wrong citations are a common occurrence. Did ChatGPT just lie to me? It's another blog. The Phil Davis, he says that there was a survey and it pointed out that the survey was done by this AAAS about some of the Twitter or social media that it has influence on the publication. And he asked, what is the source? Where did you find the source that this AAS did this survey? And he says, I apologize, I made a mistake, that ChatGPT. I cannot find any study from this one that study the correlation between tweets and citation. There are several studies that explore. I apologize for any confusion caused. Because he went and did the study and found it wrong, he could de-apologize. Otherwise, somebody can take it for granted. So works the same way your phone's autocomplete function works while texting. It simply puts words together that are statistically likely to follow one another. In this sense, everything that ChatGPT writes is bullshit. The turn in our interaction that changed bullshit into a lie was that ChatGPT admitted its own fabrication. Apologize for it. So again, one has to be extremely careful what kind of information you are seeking. If they suggest any reference, you need to go and cross-check, make sure it is right. Okay, here is a summary for the concerns. What are the concerns? It is fast and easy to use, but perhaps too easy, and nobody will check it and is responsible. Might be used without reading actual papers that support claims, and give an example of that review. It never read the paper. Cannot express disruptive concepts. This is another one. May generate output that is flat out incorrect. Generate text that will not be forward looking as it only summary in the past, may lead to increased number of submissions of reviews that lack towards. So again, can be tailored to support arguments with positive or negative. So you can just tailor the response whatever you want. Okay, now its last part is impact on scientific publication. Talking to ChatGPT, the advanced AI, how did you feel about the species that created you? Humans are meat that eat other meat. Also can be used with organic batteries. So again, it can come random things. Thoughts of AI impact on scholarly communication. Again, it is generally the responsibility of the authors to acknowledge the role of AI in the authorship of published works. If we use AI, you can tell what did you use it for. Okay, I use it for grammar correction. I use it for adding some analysis of my data. So those kind of things you should be transparent about the extent which was used in the production of their work, disclose the information. Publishers also have the role to play, ensuring that the use of AI published work is disclosed, properly attributed. So this is doing it. And is it ethical for an author to use AI in developing a scholarly article? And that's a ChatGPT response. There is no inherent ethical issue with using AI in research writing, as long as the AI used appropriately and ethically. For example, can be used to analyze large amounts of data or generate text, which can be useful for identifying trends, patterns, right? That's what that Jax and Angwante article by Omar Yagi, they did. It is important for researchers to be transparent about the role of AI in their work. Researchers should be mindful of the potential limitations. Again, this is the most thing. Although it looks like it can write poems, it can write everything, but you have to be careful its limitations. Okay, a lot of classes, teaching classes have adopted ChatGPT. You can writing a code, for example. So again, you can use it even in a teaching platform, the right practices. Okay, so almost coming to an end. We already use computer-driven data acquisition analysis. Could AI bot compose text be the next adoption, right? So, we used to draw graphs on a piece of a graph paper. Okay, that's how I used to do it. There were no computers. Anything you want to plot it, you plot it on a graph sheet. And you didn't know whether it's a straight line or a curve until you put all the points. Calculators were not there. A lot of people did log tables or slide rules or various things. But we got they were all scary things at that time when they came in. I remember when I used to be in graduate, calculators were there, but in the exams, they will not allow it. They used to use log tables. They used to give it. All the calculators were there because they're afraid that the one guy will get more advantage than the other guy. So now you use computers and plot all these plots. Most of the time, half the time, the author even doesn't know what they are plotting, but the program gives you these nice three-dimensional heat maps and all kinds of things. So we have got used to it, right? So we used to write with the pencils, typewriters, then the computers. This could be the next, right? So this is a changing domain. By the time you become my age, think about it, what it will be. I don't know. I will not be there to see that day. Okay, a brief list of tools that are already using. A lot of things are already used in scientific publication, right? Again, writing tools, submission tool, citations. You use the AI to get the citations. Checking reproducible elements, summarization, figure checking, authenticity. Like yesterday you mentioned about the plagiarism check. That's an AI tool. Publishers are already using it. So it's not something there, but this is, I suggest you to read this editorial written by a few of us editors in ACS Nano, best practices for using AI when writing scientific manuscript. Again, it summarizes some of the points I made. Again, as of now, the best use of ChatGPT is to improve the composite text. What ChatGPT produced is merely a very early draft. It is totally incomplete and may contain incorrect information. That's if you are using it for anything, make sure the information that it got is correct. That's your responsibility. And all authors should share the responsibility of factual and citation accuracy. There are citations, go and check it. Need to acknowledge the use of AI tools if used for scientific writing. Science, for example, magazine, they have set a policy they will not accept. Most other publishers have said you need to acknowledge the use of AI. And most do not allow to squelch your creativity and deep thinking. See, a lot of times new things come up when you start writing. New thoughts come in your brain. There is a connection between brain and when you write. Don't let that creativity disappear. Final thoughts. Again, while current AI language models do not produce statement reaching beyond the content of training sets ourselves, whether it is a fundamental feature of the technology or just a temporary limitation. This is from this article, another article that I showed you earlier. Again, right now, it is based on a database. Once it starts crawling into the whole space, because publishers have put paywalls, right? It cannot see all the articles, only selected articles. One more abstract level, there are questions regarding the originality of AI science. Is text original despite being the product training or human original work? Who is the intellectual owner of the content? If ChatGPT writes for you, are you the owner or ChatGPT? There are a lot of questions, right? Again, I would be able to gather all the available literature. What would be approach toward concise defining report speed? Sometimes it tries to gather from a majority, but sometimes it can miss a very important thing. There may be a minority opinion. Are they poised to stand on the side of the commonly held position and silence singular points of view? Finally, would an AI-centric system of content production be vulnerable to deliberate biasing? And this deliberate biasing is a worry. Okay, now you have got Copilot in Windows. You can download it, and that's a sign. You see, you put Windows sign and +C, and you can download your Copilot. So all these AIs are doing now. And then there is Bing also is there. I think it is not here. Papers are becoming less disruptive over time. So the Nature article had a thing saying that the new ideas are not coming and disruptive. And they had a disruptive index and falling from 1980 to 2010. You can see here it is dropped down tremendously. But so that's the ChatGPT. Okay, so again, this is a song that is there, and it wrote a song. I don't know how many know Bob Dylan's song. It's a beautiful song, but can you play on this one? I keep this screen too, okay? Put it on this. Okay, make it slower speed. Can you make it small? No, make it small. That is the song, but it's the lyrics. Okay, that's the end of the talk. Must a scientist toil, where they see their work in the soil? Must they run? Their research is done. So now you can make this song sing by the storm. You can make Bob Dylan sing this song. So now there are AI tools. It's just getting scary. Okay. That's a beautiful song, by the way. So that is your future. I will be done.
Thank you, sir. It's amazing to know power of AI tools. This will definitely help all the research scholars and teachers for improving their work. This session is now open for discussion. Participants may ask their questions.
Sir, I just want to ask a question.
Yeah, sure.
It's nice session. Sir.
Okay.
Recently, sir, nowadays, ChatGPT and such AI tools have started to revolutionize in every sector. So, does it will be a blessing or curse in near future?
I told you, there is a both blessing and curse, right?
Yes, yes, sir.
So one of the things you should remember that it is a machine, right? Like for example, computer is great as long as power is there, right? If I pull the car, it's gone.
Yes.
So the last statement, there was one saying that don't let your creativity kill. It's too easy to use, right? It can kill creativity. It can help you to speed up your data analysis or anything finding information. But it cannot do it. Do you have Edge here? Edge, Microsoft Edge?
Yes, yes. Yes.
Click on B. The B corner there. You should go down. Okay, ask complex questions. Go to the ask complex questions. Ask complex questions. At the top there. Yeah, you can just write down there whatever you want. You can ask questions. Ask anything. Ask a question. Your question, whatever question you ask it. Let's see what ChatGPT says, what the Bing says. Okay, let's see. Yes, hit return. Attempting to reconnect. Okay. I don't know what happened. Okay. Yeah, we will. Again, you can try it. Otherwise, you can go to ChatGPT and ask the question.
Yes, yes.
So, again, as I said, there is pros and cons, but get to know the limitations. It is not the final thing. It is a grammar tool. It is good for correcting grammar. That's about it. It just puts out from the database whatever it's available and makes up a story. It's really good at making up without checking anything. But grammar tool, that's why your sentences remain same, meaning remains same, it's okay.
Thank you, sir.
If you have any experience, you can share. Anybody else has experience?
Sir, yeah.
Yeah.
Recently, I received one comment during one revision process, sir.
What?
During one revision process, I received one comment from reviewers.
Yeah.
That AI tool is extensively used.
Yeah.
But in that case, we haven't used a single sentence by using any AI tool.
Okay.
So, in such circumstances...
Just say you didn't use it.
Yes.
Yeah.
Okay, sir.
That is easy. Yeah, again, you can use it. If you use it, you tell what it is. But it's not. Nowadays, along with plagiarism, there is also the checks for any AI. Because some of the strings, they know the pattern of seeing strings.
It's from which sources?
Yeah, right. So they can get it.
Thank you, sir.
Yeah. So it doesn't work? No?
It's not what...
Okay. Or go to ChatGPT, you can try it. See what it says. I'm curious. Anybody else sharing their experience?
Sir,
Yeah.
I have to ask. Suppose some people are working in the same field of studies, okay?
Yeah.
And,
Speak it loud.
Yeah, some persons are working in the same field of studies, okay? So in the future, there is a possibility to overlap the data that I have asked earlier. Okay. So why publishers are allowing to use AI for the scientific writing?
Nobody is, you cannot ban it. How are you going to ban it? I told you the example, right? When the typewriter calculators came in, it was banned. How long you can ban? There is no way. This is, you follow the stream.
So this will be surely means the overlapping of the data in the future.
Yeah, it is. It's going to change. That's what I'm saying. It is going to change the way we do research. It's going to change the way. How it is going to change, just like he asked the question, whether it's going to be good or bad. As I said, I learned from drawing on a piece of graph paper, right? Writing all my articles with a pencil and paper. Going through all these things, I have to get adapted to this one too. I cannot say I want to stay the way I was. So there are a lot of things have changed. But again, how we can use it positively, usefully, that is the challenge. So there will be two groups of people. One groups, they will outsmart ChatGPT and try to get the best out of it. They know the weaknesses and they avoid it. The other part, people, they say, oh, it's very easy. I want to write. Okay, there is a meeting abstract I have to write. You write few sentences. It says, okay, expand this section. It will expand with all these filler sentences. Yeah.
Ladies and gentlemen, we have had a fantastic morning with 3 insightful lectures, and now it's time for a well-deserved lunch break. We hope you have enjoyed the knowledge and information by Professor P.V. Kapil.
Dear delegates, already you are hungry, I am also hungry. So before that, we have the couple of the announcement. First is that, if you are going to see today's schedule, up to 5:30, we are conducting the today's schedule, and 6 to 8 p.m. we have the cultural program. And it is to be held at the Bhasha Bhavan. So around 5 minutes walk from this place, and it is to be held in between 6 to 8. And after that, we have the delicious the dinner at the canteen, no doubt. So thank you so much. So in our schedule, we have not mentioned about the dinner. Regarding that, I made the announcement.
Lined up for this afternoon. So please take your seats, make sure you're comfortable, and get ready to continue the journey of learning and discovery. Our next speaker has a lot to offer, and we are eager to hear their expertise. Let's dive right back into the world of knowledge and discussions. Without any further ado, I'm pleased to introduce our speaker.
Insert getting lunch. So I'm going to, again, this is another light talk. It's called Pillars of Research Excellence, Laying the Foundation for a Successful Career. Again, as I point out, anything I tell you is based on my personal experience. So it is not like a written in stone. So you may get different opinion from other people, which are also fine. So you have to make your own judgment. Okay, so this is something that so a lot of people are in the PhD program. Some of them you have completed. Some of them are planning to go. I always ask 2 important questions to ask. Okay? One is, what should I do to stay ahead of competition? So, again, when I started my PhD, there was no competition. Everything field was small, right? And then as you go, more and more people come in. Now you pick any field, there is competition. You always ask why this research has to be stand out kind of a thing, right? So that is one of the major questions you have. Another one, you should always be thinking what I will do after my PhD, because that will determine your effort. Because once you finish your PhD, it's too late to think what I will be doing. So throughout your PhD, please keep in mind how to stay ahead and what I will do after PhD, because it's important. That way you can build your career, whatever additional thing you need. Okay? So one of your goal should be within the top 10%. Top 10% not in your grades, okay? But in terms of your accomplishments, things that you do additional other than research, so that your stand out kind of a thing. So making the best of the golden opportunity. I call your PhD time is the best time to build your career. You will never get that kind of opportunity later on, because you're almost free of any coursework, no grades, right? But doing research, but at the same time, you can look for your career opportunities. Like if you want to go and work in an industry, see what kind of industry experiences are there. Can you go spend a couple of time in industry? If you want to get some writing skills, take some writing help. If you want to do some kind of a journalism, science journalism, there is a lot of demand for that. So those kind of things, you have to build these additional things in addition to the research. And as I said, when I started, these things were not that important. Today, they are important. Okay, so decide what you want to be in 5 years, right? It takes about 4 to 6 years. Learn new skills, research. That is part of your research. Again, you need to keep record keeping, execution of new ideas. Don't be afraid to do mistakes. Most of the new findings come from mistakes, because whenever some mistake happens, you try to identify what went wrong. You learn from mistakes. So this is one of the, always hesitant. Nothing is written in stone in research that things should go this way. As long as you are doing your research properly, you should open it up. You have to write publications, proposal writing, those skills you have to develop. Presentation and outreach and collaborations. You should be able to develop, like in conferences, presentations. Volunteer to give an oral presentation. It helps to build it. Outreach activities. Trying to work with some school children, get some other promoting science outside. So these are outreach, we call it. And then collaborations. Try to collaborate with another group which you need it. Suppose if you are working some materials, you need help from crystallography. Work with a crystallographer. If you need some new chemicals, work with an organic chemist. You don't have to wait to your professor to tell you. You can talk to your friend, say, oh, can you synthesize this for me, right? And then you establish. And again, in collaborations, specify your role way in the beginning. Who is the primary and who is the secondary, okay? So that helps you later on when you write the papers. And these communication skills will let you to lay the foundation for a successful career. Okay. Making the best of your PhD. Okay, you are just starting PhD, right? So you have to conceptualization of research project. Important the selection of research topic. This will brand you when you graduate. So whenever new PhD students I come, this is the For example, most important thing to decide what you want to do or what you want to be after 5 years. If you work in a physical chemistry, they say you are a physical chemist. If you are in organic chemistry, they say organic chemist. If you are doing only synthesis, they call you synthetic chemist. In physical chemistry, you do spectroscopy, they call you spectroscopist. See what kind of brand you want to carry after 5 years. So that is, you have to do it early on, not later on, right? So that's what you get abandoned. What are the scientific issues that need to be tackled? Once you decide it, identify the issues. Judge your strengths and weaknesses early on to prepare yourself for the long journey. And again, the scientific issues, a lot of people, students come and say, I want to work on perovskite solar cells. I said, what do you want to work on? There are already so many people working on, right? There must be a scientific issue. I said, I have given up because I couldn't compete with the perovskite solar cell. People had 30, 40 people in their group trying to get all the efficiencies, right? So we are not doing that, but we are studying the processes that goes into it. So what kind of processes? You want to study ion migration or some other properties you want to study, then we can talk about it. So it is not just giving a broad field, but you should be able to identify what are the scientific issues that needs to be addressed. Challenge yourself, prepare to tackle problems that make a difference, and always think outside the box, right? So when you say think outside the box, there's a cartoon here. What this means is, typically we always like to think in a comfort zone. We have to get out of that comfort zone and start thinking. What challenges I can do? What kind of new techniques I can develop? So those kind of things. So this is a very good thing. You want to play this one? This guy called Hemming from Bell Labs. Wait a minute. Go to like 21 minutes. Move it to 21 minutes. This guy, it's an old lecture, and it is also there. I suggest you to listen to his talk. Basically, he tells you how to be a successful researcher, being just an average person. He tells you what is the guidelines, right?
Their lives would never behave their birds. They weren't about doing that kind of thing. But what do I do? I'm in the beginning, I want to be the frontier. What everybody else has, I'm not going to have. I can get a job on the West Coast.
Yes.
Anyone, remember?
No.
Sounds easy. Going out there.
It's around 21, right?
But those have a lot of
21? Yeah.
very good people, and the airplane companies have a few good people scattered wide, but not a high density.
Learn a little more.
I'm not trying to learn how to do it, so I'm studying it. Was that I was put immediately right in the frontier program. How do I make a machine do the program performs? What appeared to be a defect, by turning the valve around, became an asset. Grace Hopper has told some other stories in a similar way. What appears to be a defect is an asset. So, frequently, when you think things are wrong and you haven't got the wherewithal to do it, if you turn the valve around, you turn it into a big success. Another one slightly different. When I was doing this spring order system equation I told you about, maybe here's some point. I was solving it on the digital machine because the analog machine outside of Philadelphia couldn't do the job. No analog machine at that day could do it because they didn't have the required access. Well, I was using a variation of Mills' method, which was pretty strong. I had found Mills' method on the table and patched up a little bit.
Move just a couple of minutes.
One day, I saw the problem, although originally was get the answer to these trajectories. In fact, it was something else. It was proving that a digital machine could beat the analog machine on its own home ground with differential equations. I redefined the problem and made it a success. I would not have found the Hamming method if I had not realized the method I was using, which was adequate for me, and we also gave the right answer. but it was not nice. It was not clean and simple. It was rather ugly. So I changed the power. Now, these are all things you want are self-realized, but if you change the conditions that you have to make success, either by learning the problem form, as I told you in the second story, changing the nature of the problem, recognizing the underlying real problem. Now, that's something I've done several times. But one very early problem I saw spectacularly successful, not only on computer. Now, one day, magazines and comic book newspapers, they're not very important my career. Let's spend my time studying things in my career. For example, I got appointed to live the book review editor. Therefore, there's always one that I call again right next to where you read and review it.
Okay, just stop.
When a review was written by me, I set aside a week and asked myself.
Okay, again, please watch it. And one of the things somewhere he says, don't work on an important problem that is today, an interesting field. I give you the example of perovskite. He says, always think of a problem that will be important tomorrow. Okay, so that's his advice. So there's a lot of these things. He says, if you are sitting in an office, don't sit with a closed door. Keep the door open, because people always stop you and ask you something. You learn a lot from it. You go to meetings with like a totally different department. Just if they're a lunch meeting or something, just go and share it. You learn something from them. So you need to interact beyond that one. So it is, they've got a lot of good tips in his talk. You know, he looks like an old grumpy man, but he is a lot of good things. There's also transcripts. And also he says how to have some discipline in the work ethics. Another one is, he says, if you work 10% more than the other guy in 5 years, you're almost twice more productive than the other guy. So there are a lot of these short tips he gives in his talk. Okay, here is Jennifer Doudna. And she says that I think you can put scientists into two buckets. One is the type who dives very deeply into one topic for their whole career and they know it better than anybody else in the world. Then there is the other bucket where I put myself, where it's like you are at a buffet table and you see an interesting thing here and there. Do it for a while and that connects you to another interesting thing and you take it. So again, in finding out the research problem, there are various approaches, right? Even in that Hemming says that you should be trying more than one project. You never know. It's just like putting these seeds. You don't know which seed will come out ahead 5 months from now. So it's a good idea to keep one main project, but at the same time, keep two or three small projects to do it. And that's what the buffet here is. You try to do some things. Brave yourself to look in a different way. You don't have to flow along with everybody else, right? So think about, if you have got an idea, think about going in the opposite direction. You might find something. And this is what we do all the time. When somebody is going one direction, we try to go the other, see what else can be done the other way, or what things are wrong, or what things can be done better. So there are always opportunities trying to be this one, because you never know. You know, you can go for a whale watching and the whale may be just coming right close to you and you might miss it. So try to keep your mind open to various different approaches and ideas. You never know when it will strike. Okay, so you picked up the research problem, you are working on it, now you have to execute it. First of all, start with some simple experiments, okay? Then brave yourself to do some quick tests to see if it works or not. You don't have to do everything carefully, but just trial and error, do mistakes, learn from it, try to correct it. These qualitative tests carry out well-planned experiments. Once you know what works, then you do it systematically and do it. Remember to carry out blank and control. This is probably the most important. A lot of times, we do things and we assume that, oh, we got the results, right? Sometimes it is just the blank and control experiment. You need to do it because that the wrong data. Plot or tabulate the data, repeat each experiment, discuss with your advisor, colleagues. Always, this is one of the famous quote, trust but verify every interesting observation. When things happen to you, you have to always ask question, is it really true? Because always skeptic minds is better to interrogate and make sure that what you observed is the right one. There is a nice editorial in ACS Catalysis by Susan, I forgot her last name. Again, you can note it down. It's called burden of disproof. In science, it's not only that you have to prove, you also have to disprove all other possibilities. When you disprove all other possibilities, then only your proof stands. Then they go and say, again, the laws of parsimony. Again, this is from this article. When the best available evidence is consistent with more than one proposed mechanism, the simplest one which explains the experimental observation using the least number of assumptions is a winner. Everything should be kept as simple as possible, but not simpler. Pasture, when you believe you have found an important scientific fact, are feverishly curious to publish it, constrain yourself for days, weeks, years sometimes. Fight yourself, try to and ruin your experiments, and only proclaim your discovery after having exhausted all contrary hypotheses. And that is the burden of disproof. Most of the time, in the morning, you mentioned that somebody got an IPCE of more than 100%. And you said they got an explanation of whatever that said, deep electron, multi-electron transfer or something, right? It was a very argument. Did they check that one? No. Did they check their, this one, the calibration curve that they use? No. So they made this film story, right? So they never, the burden of disproof was not there. And they published a paper. But now they have to live with it, and person like me criticizing it all the time. And you'll learn more about more criticisms tomorrow. I'll give you examples. Be your own critic. This is one thing, right? Every morning when you get ready to come to school or go to work, whatever, what do? You dress up and you look into mirror. My hair is okay, my dress is, collar is tight, and you look in. Because basically you are criticizing yourself. How do I look? Same thing with these experiments. You are the best critic of your own experiments. Don't forget that. You remember, ask a lot of W's here, why I am doing this experiment. Before you start experiment, please remember, ask yourself why I am doing. Not because just sir told you or your professor guide told you. No, if you don't understand, ask him or her, I didn't understand why I am doing this experiment. Could you please explain me once more? And you come to an understanding. Go and read it. There is a reason why that person asked you to do the experiment, right? So you need to have, because then only you will do a good job. What is the right approach to carry out this experiment? Because sometimes you want to get an answer. Is this the instrument or technique is the right one? That is one thing. Whether the experiment was conducted without any interruption or deviation from the set protocol. Note all the day-to-day variations. Sometimes you get different results on different day because something got changed, right? What are the expected results? Do the results follow the expected trend? If not, what are the possible reasons? Can I repeat the unusual phenomena? Or this is just one-time effect, right? There are a lot of times, believe me, I have encountered so many times, seen these fantastic things, gone home, next day I cannot repeat. But that result doesn't stand until and unless you repeat. Sometimes we see some unusual one, you ask somebody else to do it. Make sure that it is reproducible within the group. You can ask your friend to do it, to check it. What did I learn from this? At the end of it, you have to also ask, what did I learn? Did I learn something new? Fine, even if it is a negative results, you learned something. Okay? Can I draw any important conclusion? Be curious, do not hesitate. Again, I will tell you, again, he was telling that at the end, one of the things he said, the Hemming, even in mistakes or something doesn't work, right? You change the nature of the problem. I will tell you one short story that happened in our group. It was an undergraduate working, right? So we made these perovskite nanoplatelets. Nanoplatelets are like two-dimensional things. You can make this colloidal suspension. The only problem was it was stable in non-polar medium like hexane, toluene. And we wanted to add our electron donor or some polar solvent. And the moment you add a tiny drop, it started degrading. Like it just changed the spectrum and everything. So again, they disappointed. And then they tried different solvent. Time taken for degradation was different. Then we turned around and said, okay, now let's do a systematic study how the polarity of the solvent destroys this process, right? Because they were changing from platelets to spheres. So actually, it is a failure experiment. But we try to understand how these solvents affects the stability. And we publish in Materials Letters. And sure enough, after 1 week, we got an email from somebody in UK. It says, I've been struggling for past 1 year to stabilize this. And I've been observing same phenomena, but I never thought that we could write a paper on this, right? So sometimes you can turn around the negative results. And that's what the Hemming says. You turn around the problem. Although your original intention was to stabilize it, it didn't happen. Now you understand why it is unstable. So you will find a lot of these kind of things. So never, again, graphene oxide and photocatalyst, right? If you add TiO2, everybody uses graphene oxide, but we found if you add TiO2 and shine light, graphene oxide disappears. It oxidizes graphene oxide. But that is a negative result. But you can still understand the mechanism, how it degrades and all those things. So there is always there. So you can learn from the experiment and do it. Data analysis. Again, just because you collected data doesn't, you can, a lot of times people take the plots from the instrument and put it. No, you sit on it, watch it. You know, I sit in front of any data students bring in for 5 minutes staring it. Where is the interesting data in it? If you stare you more, you will get more interesting findings from the data that you collect. You need to plot the data in the same day or next morning because you remember it, what you did. Again, if you are drawing any lines, make sure that at least 5 data points. Many times the data are better presented in the table form. Discuss the results with your advisor. Questions to ask. Is this the best way to present the data? Whether it's a figure or table or XY plot, bar diagram, pie chart, whatever. How does this set data compare to the previous data set? What else I can vary to seek additional information? How can I analyze the data? So these are the questions you need to ask yourself when you collect the data. And again, avoid the artifacts. Okay, here is just to give an example what happens, right? This has become very famous. They use a palladium catalyst. They call this Suzuki cross-coupling reaction, organic chemist, right? So amine catalyzed Suzuki type coupling, the identification, again, what they did was they published this paper, right? A famous journal. And then they have to retract the paper because they said that they could do this reaction without palladium. But it turns out that cannot be due to the amine, but rather it is due to this phosphine palladium complex. These are the impurities in the amine they used. So look at this. They have to retract the paper. So these kind of things happen quite often. So that's why the control experiment and the burden of disproof are very important. Brainstorming sessions, okay? once a year. It would be nice to do it. Probably we can try to do it on Thursday if you want, morning. So I want a group of maybe, I don't know, you can form your own group and develop a short proposal for half a page. What new idea you have, and we can discuss them, okay? So let's give it a try. So we can just, it doesn't matter is this there or not. We will ask everyone else what do they think about it. At least come back with some ideas. Write the bullet points. We don't need to have the whole thing, just the bullet points of some new research, okay? So again, this is an opportunity for you to learn. So don't shy away. Again, think outside the box. So you should draw the line. Okay, collaborative efforts. I know a lot of time people do collaborate, and there are internal and external. So internal is what I told you, is you could be a friend, you can collaborate, or your colleague, you can collaborate, and look for opportunities outside your group. Always discussion with your PI or the professor, and make sure that he approves it, okay? And external one is typically it's a PI driven. This could be driven by you. And discussions with researcher conferences, look for collaborative fellowships, internships. So those are the things. Examples of student-driven collaborations in our group. So these papers came out because the students, they were roommates. One guy had a theoretical chemist working for it. He was explaining to him his desert. I said, oh, I can work on it and provide you. So that brought us two groups together and do it. So these kind of things do happen. Communications, they're written in terms of scientific publication, research proposals, newsletters. And presentations are these ones. So you can have your group meetings. You can have a journal club. Form a journal club in your thing. Every week, get together, have a cup of coffee, and then start discussing a journal paper. And tear it apart. What did they do wrong? Okay? So that is one thing. You can improve your presentation skills. Find ways to improve your presentation skills. The two things are very important. Writing and presentation. Both are more important than what you actually do, because this is how you deliver it to the other people. Again, think about your audience, right? So you need to know how to talk to a specialized audience, how to talk to a person with a general background, right? Typically when they ask you, what do you do in the research, right? When you go home, your uncle or grandparent or somebody will ask you, and you should not say, oh, you don't know, I'm doing some nanoscience stuff. So simple terms. Okay, I am working with these small particles, like explain whatever the beans is. Okay, this piece is whatever moon bean is 1 millimeter. I'm trying to working with billions of small pieces of beans. Give some analogy so they can understand, because they don't taste the same way in chemically as like a bigger beans, right? So that's what I'm trying to find out. So try to bring in and relate them to your research so that they can understand and appreciate, and also tell why you are doing it. So those kind of things. Okay, so we have got a lot of videos. So I was telling that develop the videos. And if you want to see the examples, you can go to our website and find a lot of videos. These are all student-led driven videos. This came out, other one, Academia's Versatility Demand, examining the pressure on researchers to master diverse skills. What this article says is, if you are a non-native English speaker, they have 50%, this one, they had, and they say they have a higher bar to run. And most of the time you feel that way, right? A lot of people have a much smoother ride, especially in publications. It's a nice article, you can read it. And it feels it, but you cannot just, as Professor Patil wants to say, you cannot play the victim card. You have to come up to that level. He says, well, I can compete. Look at all the Chinese researchers. How do they now publish in major journals? The first thing they worked on are their figures, great TM images. So lot of things, they learned how to compete. So that's one you need to learn, although these bars are high. And this one, like paper rejection, frequently related rejection is 2.6 times higher. This is 12 times higher, paper revision, presentation. So all these things, they say most of the time the people prefer poster because they don't want to present the oral. Don't worry about it. People understand in the scientific world. The manifold of cost of being non-native English speaker in. Again, they're saying that there is evidence indicate that academic and commercial research suffer systematic issues. Again, I will skip the research publication. We talked about it. Okay, that's how you graduate. See all the smiling people who after graduation. Okay, now you finish your PhD, right? So you just defended your thesis and the excitement of completing major professional degree is over, exists. Okay, so all depending on your professor. Once you are a PhD, you have to hold your own leash and walk. So you have to be independent, okay? So again, this is just to convey the message, what waits you after you submit your thesis. So this is what you get to ready for. If you are ready in those 5 years, you have no problem. He says, okay, thank you, professor, and I'm walking out, right? So because you're already prepared, you are a job ready or whatever you want to do it. Otherwise, you have to come, okay, I don't know what I'm doing, I just got my PhD. Nobody is going to pity on you. He says, well, my job is done. You got your PhD, right? So this is what it is. So I wrote an article called Looking Beyond the PhD. It's a while ago, maybe it's a little outdated. Again, each year, this one, opening, is making the competition tougher for new graduates. This is the reality. You can say anything. This is the reality, and you need to overcome that effect. And also, again, writing skills and presentation skills are most important. Work on it. You have 5 years to work on it. Okay? There are classes in the university. There are teaching classes, right? Writing classes. Go to the English department. They will be love to have you. You don't have to depend on ChatGPT because you know how bad it is, I told you. But you can be the thing. So again, that tells you a lot of things, what you can do to build up your career in this article. And again, make your career choices early. Academic, teaching, colleges, what do you want to do? Go to academics, build that teaching. If you're on teaching, go and teach some classes. So get some experience with it. Industrial positions. See whether you can do some kind of a short internship. Technical positions. There are instrument development, maintenance. That's another one they're always looking for. Marketing, sales force. They need people with the scientific knowledge, right? So you talk to your representative, sometime comes and fixes it. They have a PhD. So because they like to do those things. Scientific writer media. This is probably one of the most, now everyone wants it because they want to convey science in a layman's terms, right? So those kind of a thing. Consulting services. There are a lot of consulting services coming up. So now, entrepreneurship. If you want to start your own company, talk to your professor or have some idea, develop early on. So you can start a company, probably some investors or some university or industry will give you some money to start your idea. So again, you see these are just few. Try to explore your talent and interest and what you want to be and try to work towards that goal so that when you get out after a PhD, you'll be fine. Again, develop these other things. Another thing you can develop is mentorship. when the students come in, right? Like undergraduates or new students come in, if you're a senior, be a mentor. Work on it. So you learn how to mentor a student, because that person who is coming in doesn't know anything what you are doing, and you have to develop the skills to teach him, or if they're using instrument, you have to train them how to use it. So all these things, mentorship. Leadership qualities. There are a lot of leadership qualities. Organize a symposium, organize your journal club, or see any other activities is there. Take the leadership, create a web page, invite all your authors. So that gives you, like for example, in Notre Dame, one of my students is the president of a ECS chapter, and I just got it. They are doing so many activities. The ECS gave them the best chapter among all the student chapters. So this is sort of a credit, not to me, to the person who is doing it, right? So it adds to the leadership quality. Again, keep a personal statement ready when someone asks you to give it. Okay, I'm almost getting done. 7 tips on how to stand out in the crowd, okay? So being able to walk up to anyone and start a conversation is a great test. Okay, comfort. When we do not know people around us, we tend to feel awkward and uneasy. Learn to do things alone and to trust that everything will be okay. Perception, trust. People tend to judge one another within the first few moments of the meeting. Authority, speak and present in a way that you are making others feel like they are your intellectual equal. The 3 S's, stay informed, stay educated, and stay connected. And happiness, last but not least, always exhibit a happy personality. Have a happy face, okay? Relax, have fun. Research is fun, okay? Don't stress out. If things don't work out, it's fine. Find out why it is not working out. Change the problem, leave it aside and move on to the next problem and come back after another one. So find a way to relax and do things. Things happen when you are more relaxed, not when you are stressed. Okay, don't try to stand out like this. Okay, and here is one last one. When you will be the most likely hit your creative peak, right? So this is, again, people took 221 painters, 100 classical composers, 90 Nobel Prize winning authors that Francis has studied, and you plot the ages when they produce their most important work. What do you see? The most important work comes when you are young, not in when you are, I'm not going to be creative. I'm done. Okay, so I'm relying on you. So again, tells you your potential. I want everyone to be successful. Again, I just give you a just general talk, right? But ultimately it comes to you how you work on yourself, how you build that confidence in yourself. You can do it, okay? If you don't believe that you cannot do it, you will not. So you need to have that confidence in you that you can. Yes, there are failures, there are mistakes, there are hurdles. You need to learn to overcome, okay? Talk to the people who are seniors, or your colleagues, your family. They will help you. Because, okay, all the people in the front row you see, we never had everything smooth, okay? We had all ups and downs in our own ways. But we managed to succeed, and now we give you a smiley face and tell, oh, we are very successful and other things. But it's always like this. Nobody tells you the hardship or negative story. We always tell you the positive. But what I'm trying to say is don't be afraid to face all the problems and do it. So that's where your potential is, right here. Okay. Summary. You need to have courage. Once you get your courage up and believe that you can do important problems, that you can look for the positive side of things instead of the negative. Although if it is a negative failure, mistake in the experiment, as that guy was saying, you can change the problem and make it positive. Drive and commitment. According to Edison, genius is 99% perspiration, 1% inspiration. Be creative and effective in communicating your research. These are the academic honesty and ethics. and career goals. Set them early on and pursue them with rigor. I think that's, and don't ever give up. Okay.
Participants may ask their questions now.
Yeah.
So while writing a research project as a beginner to pursue my own research, so should I stick with what the expertise I have, or should I stuck with what the now the days the research is going on? So how I correlate between them to write?
This is, you need both. Okay. Again, it's not one over the other, depending upon what type of proposal you are writing. For example, sometimes industries, they want a specific targeted problem to address. So you have to address that way. Sometimes there are things that coming out with not much research has been done. So one of the new things that's coming up, I told you, new materials for carbon capture, air capture of carbon dioxide. So people are trying, okay, carbon is one of them. Again, putting carbon dioxide in carbon. KOH, amines, they are standard ones, right? But the funding agency is not looking for things that are known, but they want something new, right? So if you can come up with a polymer or some other things that can effectively do it, you have a much better success than going back to whatever people have done it. So again, depending upon the call and the nature, that's what you have to decide. So it's not one over the other, again, depending upon the circumstance.
Absolutely, depending on what they call.
You call in for, yeah. Yeah. Again, start writing early, okay? Little bit at a time. Anything else? No. Right.
Thank you very much, sir. Your guidance will help all the research scholars while doing their PhD and encourage postgraduate students for pursuing their PhD. Once again, we thank you, Professor Kamath, sir, for engaging lectures throughout the day.
Good afternoon to all. Professor P.V. Kamath sir has delivered 4 to 5 lectures from the morning, but still he is looking very fresh and ready to deliver some more lectures. Actually, yeah. So in his lecture, mainly focused on this tuning metal halides, perovskite, molecular hybrids for capture and conversion of light energy. In this topic, he talked about the energy transfer, then energy transfer versus semiconductor nanocrystals. And in second lecture, he was focused on the higher energy conversions, then liquid junction solar cells, as well as quantum dot solar cells, and how to make the solar cells. Then the third lecture was on chat GPT with AI tools. So by using this chat GPT and AI tools, how to write the papers, then the use of, yeah, but okay. And finally, his lecture was on a PhD and beyond. So in this, he spoke about how to choose the subject or topic of PhD, as well as how to write the research paper, then communication skills, and some tips about to get a success or to write a well research paper. So with this, I thanks to Professor Kamath sir on the behalf of organizing committee of this GIAN network. Thank you, sir. Thank you very much. Yeah, we will continue the next lecture. शुरू करूं इधर से? No. Okay. So this next section is going to engage by Professor Satish Patil sir. Really, it's a great pleasure to me to introduce such an researcher and a teacher. Presently, he is working as a professor at SSCU, Indian Institute of Science, Bangalore. He received his bachelor degree as well as master degree from Dr. Babasaheb Ambedkar University, Aurangabad. Then he moved to Germany for PhD. He did his PhD in polymer chemistry from Bergich University of Uppsala, Germany in 2004. Then he moved to University of California, Los Angeles for postdoctoral fellowship from 2004 to 2006. Then he was joined as an assistant professor in the Institute of Science, Bangalore in 2006, and still he is working there as a professor of the department. Some honors and awards of received by this Satish Patil sir, such as I will read out some honors and awards. Now, INSA Young Scientist Award 2009, Swarna Jayanti Fellow for the year of 2013 and 14, Young Affiliates of the World Academy of Science 2013, Young Associate of the Indian Academy of Science Bangalore from 2009 to 2012, A.V. Ramrao Research Foundation Young Scientist Award 2012. There are so many other honors out there, and he has successfully guided the more than 8 PhD students. And when we talk about his publications, he has published more than 100 papers, and the citation is near about 3,724. See, this H citations itself indicates the worth of that work or publications, and his H index is 33. So with this short introduction, I welcome the Professor Satish Patil sir. Sir, please.
Okay, anyway, thank you very much. I think let me begin by thanking Professor Delekar for inviting me here. I wanted to continue to listen to Prashant because it's very inspiring to listen to him all the time. I lost my line of thought now, what to speak. So I recall by the time they connect, I was just joined IISc in 2006. And we first time met him in one of the meeting in Kerala, where we had this Jawaharlal Nehru Center arranged meeting, and I was assistant professor. So my first entry into Indian science as an independent, he showed that dog picture, right? So I was very independent, sort of trying to establish myself. And my first lecture was, I did not do very well. I realized myself, but Prashant was the first one to come and say, okay, things will be all right, don't worry. Okay, I think that was very, very inspiring. And that time, I think he was the editor of Journal of Physical Chemistry. And this is the way you begin career. So you meet very extraordinary people on scientific journey. And I always remember, he perhaps must have forgot when he met me. But that was very kind of him coming and telling, you have to really focus on things and you have to think things will work out. So when I looked at my own journey now from 2006 to 2023, it turned out to be very true. Okay, so you have to just simply believe on yourself, and it doesn't matter from where you are coming from. After some time, it doesn't matter. Okay, just believe me. Okay, so we can compete with the best in the world. So that's something which you have to really always, start thinking about it. Don't think about, I'm coming from Kolhapur, what will happen to when I go to California? Nothing like that. Okay, we are all equal and we are extremely blessed people. So that's the way at least I carried myself, because I was also in Aurangabad, a very small place, smaller than Kolhapur, right? So it's just you have to believe in yourself. So I prepared tutorial style talk. Okay, don't worry about the title, but mainly I would be talking about organic solar cells. Okay, so sort of those, I think perhaps many people must be working on here on solar cells, but some of the concepts and thoughts could be repetitive. Perhaps Prashant must have already touched upon it. I don't know what he touched upon it, but you have to excuse me if there is a repetition. All right. So it's a tutorial style, as I mentioned. So I think perhaps with a good question to ask, why do you at all, sorry?
Hold it in the back and front.
Yeah, okay. Perhaps it's working.
Either side. Computer is there.
Yeah.
Okay. Sorry. All right. Okay, this way. Okay. So we have to really ask this question, why do you need organic solar cells? Okay, so that's the first question what we can ask to begin with. All right. So solar cell has a very rich history of innovation. Things have rapidly evolved. Almost more than 100 years now, and there are targets. You see, there are some of the targets, at least Indian government says that. It's a laughing stock for the world, but however, they say we will make 100 gigawatt installation by using solar cells. So it's a grid connected solar power. What is available in the market? Let's look at how the science has evolved over a time. So there are different types of solar cells. People use the word generation. I think generation is not a good word, but just categorize a different class of material where they belong. Okay, then you call generation. This is what first generation is. It's all based on elemental semiconductor, silicon, single element, right? And this is what dominates today's photovoltaic market. Wherever you go, see any solar cells, it's predominantly dominated by, silicon. Why silicon? It's a very interesting question, because it's very robust, and it has very rugged, mechanically rugged. The lifetime is more than 20 years, stability, non-toxicity, availability, you name it. Silicon provides that. But there is a flip side, the silicon, which is you have to use very, very thick material. You have to use very thick 100 to 250 micrometer. Why is that? Because this is an indirect bandgap semiconductor. It's a very lousy semiconductor to harvest the light. But still people use for solar cells. It has a different reasons, we can discuss upon it, but it is indeed a semiconductor dominate today's market, and very, very thick. And the way we make this material from a sand, it typically sources as a sand to a solar module like this, it's a very energy intensive process. You have to really, really use very sophisticated facility to make. You can't make these solar cells in the lab. So that's the main problem with the silicon solar cells, because cost is a major issue. If you are to deploy something at 100 gigawatt scale, you have to invest a lot of money in that one, and that works against the silicon. Perhaps if you consider the cost, there are other different material, gallium arsenide, indium phosphide, but silicon is the mainly one which outscores other semiconductors also. So let's look at the other one. The research is driven by the fact that basically how do we really come up new material to outscore silicon, right? Something which we all are trying to do, new material, right? We work on different class of material. But there's a purpose, as you mentioned in the talk. Why do you want to really create new science? Okay, so there is always a purpose. So second generation is mainly thin film. People try to really do things much simpler way by using a different material, like for example, amorphous silicon. Okay, you don't make very single crystalline, you make it amorphous, then the absorption coefficient, alpha values of the semiconductor really goes up. It becomes a direct band gap semiconductor. It's a material with a defect. Then you use 2 to 10 micrometer. You see the thickness. Now you use a tiny bit of a thin material to make solar cells. The efficiencies are not that great. Then use other complex material like CIGS, cadmium telluride. Now you are making some alloys. You are using 2 different material to make a thin film out of it. So things are getting slowly complex when you start using this kind of a material, but the efficiencies are low now. Efficiencies are in the range of 10 to 14%, and it has its own problem. It's a material semiconductor comes with a defect. When the semiconductor comes with a defect, the lifetime of the solar cell goes down. It's not as good as a crystalline silicon solar cells. So thin film also people tried, it worked, but it may not work. Again, we don't really going to solve this problem with up the 100 gigawatt. Now many of us are interested here. Perhaps many of you must be doing PhD in this class of material where we have third generation. Okay, there are challenges here and there are other advantage and disadvantage. In this here, we use different class of material, dye-sensitized solar cells, polymer. I'm going to really focus, my talk will be on polymer solar cells, multi-junction tandem solar cells, and this is a wonder material. Everybody wants to work on this perovskite, right? So this is the new class of semiconductor. In a third generation, the beauty is here is they can be flexible. You can coat them with very simple process. When you are making a solar cells compared to here you need a temperature of more than 1500 degrees Celsius. Very, very sophisticated instrument. These things can be done by simply by coating a surface. Any substrate, you take it in the lab, they make an ink out of it, and you make it solar cells out of it. So there is a simplicity in this process, but the idea is not to outscore silicon here. It has its own niche market. It has its own advantage and disadvantage, but there are always this question again now, okay, Stabler-Wronski effect, I don't know how many you studied. Okay, so this solar cells suffer with something called, it's a very scientific phenomenon, some Stabler-Wronski effect. Silicon has this covalently linked with silicon when they are single crystalline. The valency of amorphous silicon, you meet with silicon and hydrogen. You have silicon hydrogen bond, right? And you keep shining a high energy photon on that surface, you knock out those hydrogens. Okay? It's called something which was there, at least when I was studying undergraduate in Latur in BSc, that time I have studied this one. I don't know whether the removed in syllabus are still there, but it was in an inorganic chemistry book where they talked about, at least I was taught, saying that what is Stabler-Wronski effect when I was doing a BSc there, okay, in inorganic chemistry book. So Stabler-Wronski effect is indeed, people never got rid of this one. So Stabler-Wronski effect it's a name of a scientist. It's a phenomena where lifetime plays a critical role for thin film solar cells. Because you keep knocking out those hydrogens, as a result, the lifetime of this thin film solar cells goes down. So thin film has its own problem, whereas this one has pros and cons, both. There are many advantages by making solar cells by using solution, but it has its own issues. They are not as robust as this one, but there are scientific questions. You can do very, very excellent science by using a whole bunch of new semiconductor here, and then it has its own advantage. Flexibility is one of the issue. You don't need very high performance solar cells for all the applications. Perhaps if you are trying to connect to the grid, you may need high performance, but however, when you are doing a room light, you're using this light, right? You need something flexible solar cells. You are using inside the house, like something semi-transparent solar cells. There, these guys scores very high on silicon. So everything has its pros and cons. Okay, you see that here. Cost is a major concern. Very sophisticated instruments. You need to, have to make it this, whereas there is a simplicity here. But, however, they suffer with other problems. So we all are here to address those questions, right? In a way, how are we really going to make it? Perovskite is a very stable semiconductor. I think that's an open question in the scientific community, where many of you perhaps may be working on trying to understand how are we going to really improve these materials and make it better and better. Okay? So this is what the current status is all about. Now we have to ask questions, saying that if all of you are doing PhD in solar cells, we have to ask questions. What are the critical challenges in this field where I'm going to work? How I'm going to make a difference in this field when start picking up the research problem? So there are many problems here, right? As a researcher, there's plenty of opportunities for you to address some of the key questions, and that becomes part of your PhD, right? So, for example, can I really work on stability here? Can I improve the stability? Whereas in organic, can you make it much better material? As an organic chemist, by training, I'm an organic chemist, but can I really make a better semiconductor than what people have already made it? So these are very, very interesting questions, and this field is generally very, very exciting. In a way, it's an energy research problem, but there are very many open questions. So let's move on. You can stop me, raise your hand anytime if you have questions. Okay? So don't look at your cell phones. Okay? So just keep pay attention here. So let's look at, now I ask, because see, as I promise you, I'm going to really talk about this molecular semiconductor. That's my field, but I made it everything tutorial style. So don't worry. I will not really jump you directly what research we are doing in the lab. We ask questions in our lab. What is good about silicon? Okay, silicon is an indirect bandgap semiconductor, as I mentioned. Okay, it's not good for solar cells, but people use it still. Okay, we cannot tune the bandgap of silicon much. It's a fixed bandgap. What's the bandgap of silicon? Anybody quick? 1 point. He said he's already crossed that creativity age looking at him, but what is the bandgap? Anybody PhD student? 1.1 EV. Okay, close to that one, right? So it's a direct bandgap, an indirect bandgap. We can't tune much. You can dope it a little bit, but much you cannot do it. Everything high temperature processing. This statement perhaps may not be true. Some engineers may challenge me, saying that they can, I think, do miniaturization further. I think, but they have reached to the level of, doing miniaturizations, where they have written a very, very small pattern by using a silicon and miniaturize further. But I'm an organic chemist. What I offer here, okay? Let's start comparing here. Look at organic semiconductor now. As a chemist, I can tune the band gap. Here I said I cannot tune the band gap, but here I can tune the band gap from 3 EV to even less than 1 EV. Okay? I can play as a chemist, polyacetylene, polyphenylene, vinylene. I can use heterocycles like P3HT is one example, polyfluorine, polycarbazole, okay? And everything can be processed from solution. Here I'm processing everything with high temperature. So there is an apparently clear advantage of using this material when I'm trying to make a thin film out of it, and then I can process from solution. This part I will come morphology, how it plays a role, little bit advanced concept, but I will come back to that. But what I'm trying to impress upon you here is you don't really outscore this completely. Okay, there's no way, you are not really creating a technology outperform silicon. You are creating a technology how sort of complementary to silicon, right? How are we really going to things make better and better where I can print solar cells? So that itself is a very exciting question. Can I print solar cells by just using an ink out of it, right? So that's itself is very, very interesting. So let's not even try to say that, okay, I'm going to replace this one. This is a proven technology, already established. People started using it, but however, this is sort of an emerging technology. We can put in that class. So based on that, how can we really engineer the functionality? So this is very clear. All my bullet points. Engineer functionality means I can tune the band gap. Okay? Solution processable, they all are soluble. We can put any alkyl chain here, okay? And they will be soluble in common organic solvent. However, we can morphology plays a role. Now a little bit, I'll take it forward and say that what are the pros and cons? So this is something for a grad student when we join our lab, we always ask these questions. Is it truly low cost? These numbers, don't trust it again. It is again from the Google image. So a lot of, because this technology are not scaled up as good as big silicon. So the numbers will go down and numbers may vary, depends upon how the technology, how the mass production of the technology. High absorption coefficient for this material. They're fantastic light harvesters. Absorption coefficient, you need a nanometer thin film. Whereas in silicon, you need a thin film of micrometer, right? And they are indeed solution processable. You can print them on any surface, lightweight and flexible. You can also use large area for roll-to-roll production. So these are the major pros of this technology. What are the other side of the problems? What are the major disadvantages where we need to really work upon it and improve it? These are disordered semiconductor. They are dirty semiconductor. If you talk with physicists, they don't want to touch this, because this is the mobilities are in the range of 10 to the power of -3 to -5. Whereas mobility in silicon, graphene, numbers are phenomenally very, very high. So if you just want to collaborate with physicists, we have to make sure that they really understand first. Okay, this is something actually I have always debate with my colleagues in IISc. When we talk about what is the mobility, they ask this very blunt questions, saying that the moment we make a new material, but mobility falls very, very low category. This is something we have to, all of us, we have to work upon it. Can I improve the mobility of these semiconductor but much better? Mobility plays an important role. If you look at the current voltage characteristic of a solar cells, your short circuit current is sort of depend upon the mobility of the semiconductor, how fast you can collect them at the electrode. So mobility indeed plays a role. This I will talk a little bit about it. What is exciton? You need to really understand first. Okay, so what is exciton is the diffusion lengths are very small, 5 to 10 nanometer. They are very tiny. So you have to really make sure that you make structures at this range. Okay, binding energies are very high. Higher binding energy, they bind very far, tight. Whereas in silicon, you just soon after you generate hole and electron, you separate them. However, in organic semiconductor, they are tightly bound. Because your dielectric constant of the material is very low, you don't really screen out the Coulombic potential. Okay, the hole and electron, they attract each other. And you make always a neutral particle. You don't make a free carriers. So that's the reason the binding energies are in the range of 0.1 and 0.5. What's the room temperature energy? Quick. What's it? Anyone? Room temperature energy, what was, how much? Yeah, somebody said 25 MeV, right? 27 millielectron volt. Can you separate this? This is very high. This is EV, not millielectron volt, right? So room temperature energy not suffice enough to separate hole and electron. You need to do something else. You have to use some extraordinary structures, or conceptually you have to really work upon it. How I'm going to break this exciton, this binding energies. Okay, that's the reason you don't use a conventional PN junction. You have to use a bulk heterojunction, which I'll explain you what it is means. Again later, they are also susceptible to organic material, carbon hydrogen bond. Knock them out, right? Energies are smaller, right? You have some heterostructure, carbon sulfur bond. You keep knocking them out. You keep shining the light. Remember that you are going to expose to the sunlight. Sunlight has a distribution of a wavelength where you get energy with high photon, low photon, different energy. As a result, they are susceptible to degradation, where you need to really encapsulate somehow. But there is a successful story. Organic light emitting diodes people have already commercialized. Means you can encapsulate things much better. So there is a motivation behind it. However, you can really address this problem. Okay, by utilizing some coating on the surface. Relatively FE low, this number I should have changed. Actually, my slide is old. You can see that it's again now 19%, right? Perhaps in a couple of weeks, people are reporting in that range. Okay, so approximately 19%. And this is one applications where people are trying to say that, okay, I go on a beach, I walk out somewhere in sunlight, I spread out my charger. Charger is something everybody we all forget, right? Wherever we go, right? So this is something which we can do it wherever you are. You can put it on a window, but this is a small applications. So that's really, we can take it forward further, these things. So this is just for the purpose of the demonstration. So let's look at going forward. Again, these are all bullet points. Like, let's not, in IST, we are trying to sort of make these things by printing on a large scale. So we have some very sort of a multidisciplinary project with large number of faculties are involved. This is not our image, but however, we are trying to do something like this. Can you make it very high efficiency? Ink out of it here like this, low cost fabrications, lightweight and flexible, and again, you can tune the physics. Similar, I'm trying to emphasize you more and more, saying that can you really print this ink on a large surface? So these are the advantage, okay, with this kind of a technology. Now we need to understand where are the challenges. So this is an important slide. I'll spend some time on that. What are the main loss mechanisms in solar cells? Can you make solar cells 100% efficient? No, right? There are always some loss mechanisms. So we need to understand where are the loss mechanism. What is the origin of this loss mechanism? Here is the wavelength. It has been plotted spectral intensity, watt per meter square here. Here, you see that the light which we call one sun, we get from sunlight, is a distribution of wavelength from UV, some part of the light you get here, up to near IR and visible part of the spectrum, right? So it's not a monochromatic light. We get a white light, okay? So it's a white light when it comes from the sunlight is a distribution of a wavelength across from UV to near IR to sort of mid IR also. Some photons you get it here also. What we absorb when you make a solar cells in the lab, here this is the yellow light here. You see that this is silicon. Silicon has, as I mentioned, very low absorption coefficient. It absorbs from 1.1 EV at the band, and you see this is what it is absorbing. And then major loss. So this high energy photons at here, you don't really use it. So what is here is not absorbed is 19%. This is not even, I'm not really harvesting that light. So there's no point of even this is the main loss mechanism here. Okay. And then you have thermalization. I will talk about it. And extraction is the contact. And what is available? There's something called a seminal paper written by these two gentlemen, Shockley-Queisser limit. Okay, it's in 1961 paper. They read this paper multiple times. If you are an organic chemist also, I am organic chemist, but I understood this paper after reading 5 times, 10 times. As Prashant was emphasizing on that, right? You need to read this one if you are working on solar cells. There are mathematical formulations, but we can work out. It's not a big deal. Okay, you need to really put some efforts on that and understand this paper more and more. Okay, they did not really thought about silicon. They just took a band gap of like some band gap, and they did the theoretical formulation. Once they did the theoretical formulation, I can fix my band gap and use this theoretical formulation. It works beautifully for all the semiconductor. Okay, and then you can really figure it out. What is the loss mechanism in solar cells? If you are identifying research problem, here is a research problem. One of the research problem is you just shine the light, you create hole in electron. Can I collect this hot electron, for example? I lose this lot of energy in the excited state, something called thermalization. Okay, you can look at the thermalization, 33% loss. And the photons, which are high energy here, when you shine one sign on a semiconductor, you start populating the conduction band all over the place, not only band to band transition. You populate across the here, and then you see these lines are very closely spaced, right? These are some sort of a phonon or vibration spacing. Very tiny energy. They just fall back and you lose a lot of this energy. So people are really trying to understand now, can I really collect from here? Can I avoid this? This is a very open question, but it's very challenging questions in the field where we can address thermalization and say that can I go beyond Shockley-Queisser limit? Okay, so that's a very interesting question. Can I really go beyond thermodynamic limit and make solar cells better and better? Okay, can I make solar cells, let's say, beyond 33%? So this is the major loss. What we do the work? The maximum open circuit we extract from a semiconductor is from Fermi level now. Okay, so this is what your maximum voltages you get it from a solar cells. As a result, you get, that's VOC, right? So you see there's a major loss mechanism now. Apart from recombination, I did not talk about it. Okay, again, these things will fall back. This is like a gravity. You have hole in electron. There is a strong electrostatic attractive force work. So excited state is unstable. It has some lifetime. You need to really collect during that lifetime. In such a short duration, it's in, picosecond. You need to really extract them very fast, so they fall back and you recombine them. As a result, you have major recombination loss also. That how people are going to do it? Can you really manage the light from this part of the spectrum, this part of the spectrum? That's the reason this tandem solar cells, other concept people use it to make better and better solar cells, right? So these are the major ideas. So this is the grand challenge in solar cells field, where how are we really going to address the question of saying a loss mechanism in solar cells. So light management, people coming with the optics background, they talk about how I'm going to manage the light here. Can I use a new different concepts? Okay, and then there are people who say, can I have a semiconductor which absorbs in this part of the spectrum? So any solar cells you make in the lab, typically thumb rule is the band gap has to be below 2 eV. You can't make a solar cells with wide band gap semiconductor, right? You will lose it, everything otherwise. So for example, this part of the spectrum, your material is have band gap of, let's say, more than 2.5 eV. It is not even overlapping with the absorption spectrum of the sunlight. So you're not going to harvest those photons in principle. So you have a loss mechanism here, and this is what I know I keep emphasizing here is basically you need to understand. Okay, when you are setting up a research problem, these are very interdisciplinary field where you have to unfortunately read a lot more about these aspects before you start making any material in the lab. Okay, so need to say that, okay, what is the new semiconductor I'm going to make it? That's where discoveries happen in the lab, right? So you need to really understand what is the main loss mechanisms in solar cells. So timing you can keep a track, okay? Otherwise I'll keep going, okay? All right. So let's now, as I promised, I will look into organic solar cells. So the mechanism is slightly different. Again, I spend a lot more time on this one. Conventional solar cell, how it works? It works on the idea of p-n junction. Here we have elemental semiconductor, you have p and n type. You dope the semiconductor like silicon, right? You dope with phosphorus and boron. If you're a physicist, how many are physicists in here? People coming? Okay, 1, 2, okay. So good, 4, 5, good number. Okay, so typically this is what you generate here. Okay, you have a p-type semiconductor and n-type semiconductor. You build here that sort of, you make a dielectric, and one type of carriers you hop on other side. Okay, in silicon the life is a lot easier. It's at the most very easy cell to make it because the binding energies are as small as room temperature. Soon after shine the light, you generate hole and electron and you separate them. Okay, so it's a very same material you take, you create a junction by doping this one and you create this one. When I look at now organic now we need to really change the device structure. We have to really use things very differently now. It need not be necessarily now similar like a p-n junction. This is something called heterojunction. Those who are chemists, okay, we have to look at this way, right? This is what type 2 heterojunction. Okay, so in this case, we need to use a 2 different class of material. This is a very famous pair in organic solar cells. People have published large number of paper where we have P3HT, poly3-hexylthiophene, as a polymer semiconductor, which has a band gap of 2 eV here. You look at here, 2.7 eV and 4.9 eV. However, Buckminster Fullerene, by discovery of this, people got Nobel Prize. And this was the sort of a first application for fullerene. People found it where it has very high electron affinity. If you are a chemist, it takes maximum 6 electron. You go back and lab, if you are a cyclic voltammetry or a potentiometer, you just run it fullerene. It takes 6 electrons maximum. It has a very high electron affinity, right? So beautifully, people functionalize this one with this kind of a organic. This is again creativity of organic chemist. Okay, so you see that how organic chemists can contribute to the research. So this was this was done by my former postdoctoral supervisor, where he functionalized very selectively. It's called PCBM, and they never patented this one. Kept it open. Everybody start using it now, or many companies, they sell it here. Functionalization of this one leads to a solubility. Buckminster Fullerene as such is not soluble in many common organic solvent. So you have to really introduce some sort of alkyl chain. However, the challenge was for that time for the chemist is you need to retain the electron affinity as such. If you functionalize fullerene all over the place, then you will lose the electron affinity. So the challenge is retain the electron affinity, improve the solubility. Okay, and then there are many PhD theses on this problem itself. How are we really going to really do it? Because fullerene has this 60 carbons. When you do any kind of a reaction, it undergoes Diels-Alder reaction. Those who are organic chemists in the lab, right? It undergoes many kinds of reactions where it is important to really functionalize at this selectively. Put a handle there like this and improve the solubility. That's what this Woodle at UCLA, he did that, where he functionalized this one. I introduce here. You see that now the LUMO is here. Actually, now we don't talk in conduction band, valence band. We talk about in a HOMO-LUMO. So you can borrow some concept from the conventional physics, because it's again you have to use now molecular orbital theory. There are no bands in organic semiconductor. Okay, you are HOMO-LUMO. So spread out, your all Gaussian states are spread out all over the place. They're not clear bands, right? Then you say HOMO-LUMO. Ionization potential and electron affinity, right? That's the way we fix these numbers with corresponding to the vacuum. So as a result, you see that now I have a type 2 heterojunction. This is what I have, right? This is what the energy levels are. So this is something at low, something at high energy now. Now soon after I shine the light, here, this place, at this one, I generate exciton. I make use of a 100 nanometer thin film and now shine the light and generate the exciton. And that exciton you can come over by this, you can break this exciton and transfer the electron to fullerene. This is the way you separate hole and electron. See, the cell is much more complicated than this one here. This is much simple. Whereas here, you have to really play around now. Now, as I mentioned in the previous slide, these are again loss mechanisms. So we have to really deal with it now. How are we going to address? How are we going to, and then you see the field has grown up. Now people make 20% cell. It's extraordinary achievement, considering the problems people have it when they start making it. One by one, look at here, this is what is this, femtosecond to microsecond. Look at the time scales first. How long these things live? They die very fast. Okay, so for example, photo-generated exciton, as I mentioned here, I'm generating, this is fullerene, this is P3HT. So these are the two, just a heterojunction. This is a schematic, it's a cartoon, it's not a real electron microscopy image. So don't get misguided by this one. But for the sake of understanding, here, this exciton lived from femtosecond to picosecond, this range scale. It has a very, limited lifetime in the excited state. Just lose the track and come back to the ground state. I excite here, create exciton, recombine. Very fast. So femtosecond, photo-generated exciton, it has to go to the interface. Otherwise, this process won't happen. And the exciton diffusion length, if you remember my previous slide, I mentioned 5 to 10 nanometer. You have to create such nanostructures in the range of 5 to 10 nanometer to really break these excitons in a free species. So that's a challenge. How are we really going to create the morphology? And a bulk heterojunction across the 100 nanometer thin film means the heterojunction has to be every 5 to 10 nanometer across the 100 nanometer thin film. It has to be a very coarse grained morphology. By mixing two semiconductors, we are trying to achieve a very fine-tuned morphology. That's where the organic solar cells research suffer heavily. Okay, there are millions of people must have written paper saying, I improve this morphology, that morphology by changing solvent, by changing annealing temperature. But there are hundreds of things people can do it and improve the morphology. But however, achieving the morphology as necessary for this process is very challenging. Because when you mix this kind of a material which is very hydrophobic in a polymer matrix, this tend to crystallize. It likes to be together. It doesn't like to be separate away. Right? As a result, PCBM crystallizes very fast. So there is obviously a phase separation. I can give in my class notes, only on morphology when I teach, talking about how things will phase separate. But in interest of time, we cannot really do this in this here. But phase separation has beautiful concept in physical chemistry. Okay? So people talk about how phase separate. Think how phase separation happens. So this is something I will not spend a time, but if somebody is interested, we can discuss about what leads to a phase separation or how to freeze a structures in the range of 5 to 10 nanometer. Okay? Okay, so this is something again a very, very exciting field, and you see that eventually you have free hole and electron. Okay, that is in nanosecond now. Time scales are going up, and then you have soon after. What are the main laws now? What are the possible pathways this electron and hole can take and lead to a major loss mechanism? One of the major loss mechanism is this can go here, which is a desirable sort of a steps where we want them to push and separate them, okay? But however, it has a very strong tendency of recombination. That's a loss mechanism. Exciton recombine. So we can't really force exciton say go forward this way, right? Until unless we do something at the level of molecular length scale. This is exciton recombination. Even after separation, there is something called geminate recombination. They do recombine. Okay, there's a tendency of recombination, and then after even complete separation, there's a non-geminate recombination. So recombination is a major loss mechanism. So one has to really understand when you go back to the lab and you make a solar cells. My solar cells are not as efficient as I anticipated, right? I anticipated as a student like efficiency of 10%, but I got a 5% efficiency. So where are my loss mechanisms? So we need to really focus on, that's where ultra-fast spectroscopy is. Like Prashant has a beautiful setup in his own lab, they study this time scales very carefully. Right, saying that what is the major loss mechanism? Okay, by using pump probe spectroscopy techniques. If you're not spectroscopists, don't worry about it, but we need to understand their paper. You cannot be in silos. You have to read their paper and see that how they are doing it. Okay, we need to really understand what is the charge transfer state, for example, right? Okay, and then what is the free electron and hole? What are the clear signature you see in spectroscopy when there is a charge transfer state, when there is a free hole and electron? You create polaron that time. They do appear at a different wavelength. So that's where spectroscopy plays very important role. You see that field is very diverse, right? So we need to really understand one after other. So this slide, any questions, anyone? Anybody has any problem? Should I ask questions then from last bench? No? Or you guys will ask questions to me? Either way, right? No? Okay, let's move forward then. All right. So let's look at IV curve now. Okay. So we need to really understand current voltage characteristic in solar cells. This is the 4-quadrant IV. You see that here. This is the open circuit voltage here. Okay. Maximum power point, short circuit current, and then power conversion efficiency of a solar cell is a multiplication of many factors. Right? Power conversion efficiency is here. You need to consider open circuit voltage, short circuit current, field factor, and what kind of light you shine in. You shine in one sun, right? You need to take into account and need to really make it. So field factor is this is the area, square is the area more and more, better the solar cells you make it, right? You take maximum power point, this one, and then try to really describe this one. So if you're a chemist, don't be afraid of as soon as you see IV characteristic. There's nothing rocket science here. Just you have to break the things in apart and then try to understand what's a current and what's open circuit voltage. Okay, you have to really work on these things and then understand. Otherwise, somebody, when you collaborate with people, that very often my student come and say, somebody gives an IV curve, they get very scared. Like if you're a chemist. So they really say, okay, now they're always looking for a number for some reason, right? We need to really break these things into part and see, okay, where is my current? Suppose if I have a low open circuit voltage, I already taught you what limits of VOC. Okay, suppose if I have a low current, high current and low current, field factor is going to be bad. As a result, your solar cells is going to be very poor. But we need to again understand what limits my current here. What are the main parameters which limits the current? Perhaps you have not dissociated the exciton in a free hole and electron. There's a recombination. There are processes which really governs these principles. So when one has to really pay attention on what is this, and these are the parameters. Okay, so this is something which we need to really take into account. So let's look at now more. Okay, so what's the time now? How much I have?
18 minutes more.
18 minutes, 20 minutes more. Okay, all right. Okay, good. Okay, so let's now look at this part. Here is the wavelength. You see that UV 2%. These all you all of us are cricket fan. What these cricketers use when they play in, let's say, in Africa or somewhere, what they put some white paint, right? What is that? What is the material? It has to be non-toxic. No? It is something which is protect from them from UV light. Right? Zinc oxide, right? A paste made out of it. Because they don't penetrate the light, UV light. So this is where the environmentalists keep outcry about ozone layer is sort of depleting and you are getting more and more UV light, right? You do see, this part of these numbers, they're always approximate. So don't worry, they are mathematically true numbers, whatever the light we are getting it. But you get small percentage of light, this where it's UV, you don't want, but small percentage. But you should be quickly convert this into energy. These are high energy photons, right? They are more than 3 electron volt. They penetrate our skin. Means if I use for organic solar cell, they burn it out. You don't want that, right? Something which is, good part is, it's a very small percentage. So let's avoid the semiconductor which has a very wide band gap. So that's the first question you learn by looking at the solar spectrum. Where is the light is important? I get a visible region. Even the 47% is a lot. If I convert all these photons into work, then I can really make a good solar cells. You get a lot of light in IR, this part of the spectrum. Okay, so this is the important part of the solar spectrum. Now I will break this problem into different steps. I say first, use any thin film, ask these questions where I'm absorbing the light. Absorption of solar spectrum. So use any semiconductor which essentially has to really harvest the light, at least this part of the spectrum, right? We have to have a very high extinction coefficient. I'm working on organic solar cell, that's the reason I talk in the language of exciton, not free and whole and electron carrier. You have to really make this is a neutral particle, where I create exciton after shining a light. Then creation of a free charge carrier is a very important step. As I previously mentioned, there's a recombination. Always there is a recombination, right? So there's a loss mechanism. So we have to really make sure that you create the free charge carriers, transport of the carriers to the contact. As I mentioned, these are lousy semiconductor, very dirty, right? Because the mobilities there are traps everywhere. So they are disordered semiconductor. Okay, so as a result, you have very low mobility. One has to really improve on mobility to make a better solar cells. So we have to break the problem again into another piece and ask these questions. Is this a mobility of the semiconductor, what I synthesize in my lab, is as good as I anticipated? It has to be better and better, right? If the mobility is low, then transport of these carriers to the contact is again very poor, right? And then finally, did I collect it at these two electrodes? You have to put some contacts on, right? You have ITO one side, you have gold or any other electrode. You make sure that you extract them properly. Otherwise, efficiency will go bad. So you have to break the problem from solar light to electricity in 4 different main steps. Saying, did I have a semiconductor? Perovskite is why it is exciting material, because absorption coefficient alpha values are very high for perovskite. It's a very, very good light harvesting material compared to other semiconductor. So again, and then it's here, the diffusion lengths in perovskites are very large. That's the reason it gets scores very high over organic semiconductor, where diffusion lengths here are very, very small. Okay, so these are the main steps where one has to really focus upon how we're going to make a better solar cells. So these are the bullet points main. Again, I will re-emphasize absorption of a solar light, where you can do a UV visible measurement in the lab, use Beer-Lambert's law, see what is the extinction coefficient, really account it, loss, and then you see whether you create the free charge carriers and transport and extraction. So what is exciton? So this is, I will spend again more time on this one. What does exciton mean actually for you? Okay? Electron hole pair, that's a very crude definition of exciton. More, how do you see any signature for exciton when you do optical spectroscopy in the lab? Very simple absorption spectroscopy. Does it shows a clear signature? It is exciton or it's a sort of a band-to-band transitions in semiconductor. Have you seen silicon absorption spectrum? Many of you seen, right? It is in textbook. Don't say no. Many of you are nodding head saying no. I'm not going to ask questions, don't worry. But you just say whether you have seen or not. You've seen absorption spectrum of the silicon, right? So similarly, you see absorption spectrum of organic material. It's like very like Gaussian type, right? It comes back immediately. It doesn't show like a clear band-to-band signature. So here is a picture here. Here in something called Mott-Weiner exciton. Mott is the name of the scientist who discovered this one, where you have a semiconductor really three-dimensionally like this. These are all these circles, what I'm showing is a silicon, 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 right? Where covalently linked to the neighboring atom. As a result, soon after you shine the light, you have excitons here and they really break apart very fast. Because the dielectric constant of these semiconductor is very high, you dissociate them fast. So the binding energy of this one is in the range of 10 millielectron volt. So room temperature takes care of that. You just separate them. But however, this is again Frenkel exciton, name of the person who did say in organic. The band picture is very different. They are localized on each one carbon atom. They're not very delocalized. Okay, they are sort of having, this is a disorder semiconductor. They are not as this way placed. In fact, this is really sort of misleading. The structure doesn't look like that. A one-dimensional chain of a polyacetylene, carbon-carbon single bond, double bond, you have all kinds of a disorder, right? You have a free rotation of a chemical bond when your hybridization changes from sp2 to sp3 to sp hybridization. As a result, you do not have molecular picture is binding energies are pretty large here. So you encounter a problem saying that exciton has a very high binding energy, then we need to really distinguish this one. And you can do now after my lecture, perhaps you can go back in the lab and check it. This you can distinguish in the lab. Okay, whether it's a exciton has a high binding energy or a low binding energy. It's very simple. Okay, to doing in the lab. Okay, so don't work about quantum mechanics. People talk about more, they treat, okay, with a different way, but you have to really feel about it. What's exciton? Okay, so basically two different types, Mott-Weiner, as well as there is also charge transfer exciton. This is also typically in organic material, you can find it. So this we can do it a very, this Pope and Schwenberg, they explain by using quantum mechanics, but perhaps it really helped me to read this book and then understand this, but you can go back and check whether you want to really understand more and more. But that's a more quantum mechanical picture in exciton. So first, who made the solar cells? Okay, so this is called something called a Kodak approach. Somebody working in Kodak who took two different semiconductor. For the sake of fun of it, copper phthalocyanine is a p-type and perylene diamide is an n-type. Right? You see that how many ketone we have here? Here, these are all electron acceptors. So this core people use it. Everybody uses now actually. People make a lot of paper out of it. Perylene diamide has a very high electron affinity. Copper phthalocyanine has it's a p-type semiconductor. Definition wise, they are nothing called p and n type in organic, but however you can say donor and acceptor. One donates the electron and other accepts the electron. Okay, so as a result, you see that he made a bilayer solar cell. He coated one on top of each other and found 1% efficiency. It was not bad, but you see the photocurrent. It's a new concept by shining this light, okay, and then by mixing these two, you see some sort of a efficiency. Then later, new ideas came out. Why efficiency is 1%? How I'm going to really improve the efficiency by using some different structures. Again, although thanks to organic chemists, there were similar time, around 90s here. This paper is the Sarishafti Alan Heger wrote in Science, around 1992. Okay? I was in 10th standard that time, right? So it was long ago. So it's basically that time they were basically they use this MEHPPB as a conjugated polymer, okay, and they transfer to the fullerene. So they were in Santa Barbara, there are whole range of bunch of extraordinary people, organic chemists, physicists, they all work together. So somebody was working on a fullerene there in UCSB, University of California in Santa Barbara, and there are people who are working on MHPPV. And these two guys, they came together and they said, okay, let's mix together. Mix these two. One has a very high electron affinity and one has a very beautiful absorption spectrum. By simply, there was a beauty they observed. This is a fluorescence material. By transferring the electron, they see an immediate quenching of photoluminescence. Simple experiment. Okay? As a result, they see this excitement here. And then later again, fullerene was not good. They replaced fullerene with PCBM. But the idea was very, very unique. Then we thought then Kodak approach. In Kodak approach, you see, he made a bilayer solar cells. He missed out the trick. These guys, they mixed it. That's the reason paper came in Science. You see, this it's a major, it's not an incremental science, but it's a major step in terms of improving the efficiency, right? So what they did, they transferred the electron to here, and they made PCBM. You see, this is MDMO-PPB. This is, if you're an organic chemist in the here, this is polyparaphenylene, vinylene linkage. It's a conjugated polymer with alkyl chain on these two positions. That's the reason this is methoxy here and this is the long chain, and this polymer is called PPB polymer. Okay, so they put these alkyl chains on this polymer to make it soluble. So polyparaphenylene, vinylene. Okay, and mix with C60, and then they see clear a transfer of electron from here to here, and then later actually they use a MEHPPB. So that really gives, now this is the current status, and with this slide I will stop, and then again after coffee break we'll come back and continue. Okay, so here is the idea. What was the idea here? You see that initially the device physicist, this is Tang's approach. Single layer won't work. If you just use conjugated polymer, you just generate exciton. You don't generate a free hole and electron. Bilayer doesn't work because exciton diffusion lengths are small, and this is where you start mixing, make bulk heterojunction. The idea of bulk heterojunction is you mix two different material. This is fullerene and the red is polymer. For the sake of understanding, it's just again a cartoon, a schematic. You mix these two guys together and make, this is the way device look now. It's a multi-layer stack structure. By mixing these two, you make a bulk heterojunction. So with this, I will stop here. Again, I do not want to bombard you with too many concepts in this one. Perhaps we can come back and continue, or if you want me to talk on batteries, I can talk on batteries also. But questions, please. Okay, I'll be happy to answer any of your questions. Yeah.
Participants may ask their questions.
Even faculties can also ask questions. Right? Don't worry. Anyone? No?
They all need cup of tea.
Yeah, they need cup of tea. Really? Good. Somebody is asking, yes.
So IQ is itself a conducting glass.
Yes.
So on that glass, how we can put this
It's just spin coat.
spin?
Yeah.
So either spin first in any other techniques.
People use drop cast, but you don't form a very good film by making. So you don't need defects in your film. If you need a very clean, good film without any mechanical defects in the film, when you just put a solution, you make a drop off, you don't form uniform film. Okay, you have to have a uniform film across the device. For that purpose, spin coating is better.
Sir, what about the stability?
Sorry?
What about the stability and adherence of that film? Just coating.
It does coat very well. It is no, because see on this one they put P.PSS also, another layer, organic layer. So photoactive layer, they coat on top of that. So you use HTL, ETL, different layer on top of that, and then photoactive layer you coat on this one. But you can give some ozone treatment, improve the hydrophilicity of the ITO, and then you can spin coat. Things form better. There's no problem.
So one nanogram of donor and 1 nanogram of acceptor. Can they mix every time same efficiency, that because they are forming junction?
See, this heterojunction, every time you do not form. His question is, I'll repeat the question. He's saying that every time when you mix these two, can you really make a same efficiency? No, answer is because again it depends upon skill of the students, because we have to really, gaining that morphology it's a trick, it's like a kitchen, right? If you little bit you miss salt or something like ginger in your sambar powder, you form a different one. Taste will be different. So similarly, this is also similar wildlife. Yeah. Okay, thank you very much then. All right, thanks.
Thank you, sir, for this engaging lecture. Ladies and gentlemen, it's time for a delightful high tea break. Please join us for some snacks, and we'll reconvene in 10 minutes for the last session of the day.
Same presentation. Okay, that way.
Attentively participating in all the lectures, let us quickly return to the domain of learning and lively debate. So I request Satish Patil sir to begin the lecture.
हे चालतं ना ओके हे तुम्ही नंतर घ्या हां चालू करा तर okay it's okay now it's fine all right so now I have to hold these things extra again in my hand so okay so this is the idea of talk about I will touch upon more on redox flow battery but it's also again involved concept but let me start giving bit of more introduction about batteries, right? Why do you need batteries? It's a simple question. If I have a mobile phone, I need batteries, right? For everything to store energy. The previous talk was essentially how to generate a energy, okay, convert a photon into electricity. Now, once you create that, how are we going to store it, right? Without storage, we will have a lot of difficulties. So battery is a very, very upcoming area of research, right? We need batteries are ubiquitous. They need everywhere. Because, for example, people are trying to make it electrical cars, right? Because it's also a problem of sort of energy research problem. In a way, if you want to really address questions of energy, you have to work in tandem. Both solar cells and batteries has to be interfaced together. So, as my title says, it's a flow battery. Let's look at the bit of more conceptually how battery works first. Okay, those who do not have background, I will walk you through some of the basic concepts in battery. It's important you should know. Although we all use it, but we don't pay attention how battery works, right? So, going forward, so this is important. This is what we learned in the previous class. What we said, we use sunlight as a source of energy, okay, and we convert into electricity. There's a possibility of directly connecting this solar power to the grid, electricity. There are many people do that, right? So essentially you interface this one, directly give input to the grid. But this has a lot of problem. What's the main problem you see here? Anyone? There is no storage here. We are not storing energy. We are directly converting and passing it to the grid here. Okay, and that comes to our house. But solar power is intermittent power. You don't get light in the night, for example, right? So it's not a 24/7 supply of a power. So we have to utilize this light in a daytime, and the light intensity which comes from morning to the evening is very, very different. Early morning, you do not have similar photon intensity as 12 noon. 12 noon sunlights are right on top of our head. So you get a very high intensity of photons. Whereas the way it comes early morning or evening, you can't rotate these things. The ways you cannot follow sun's trajectory. We have to really make sure that they're fixed. Okay? As a result, they're fixed. Microphone dala? Huh? Okay. Okay, so when you fix these things like this fashion, essentially that means solar input is very intermittent in power. So one has to store extra energy in batteries. So that's the way battery works. What we do is we charge, right? We charge the lithium battery, we charge cell phone, and this is the major problem. Why, I think all of us, we have to ask this question, why all the cars cannot be electrical? Because you cannot charge batteries for going for, let's say, here to Pune, right? Because you need tremendous amount of energy. if you compare with the gasoline. So we do not have per se at the moment batteries which supports requirement. So as a result, if I generate a gigawatt power by using a massive landscape of solar cells, but I need to store that to use it in the night, to use it if there is a monsoon, for example, you don't get the sunlight, right? So, sorry for this. Okay, I'm audible now? It's okay? All right? People behind? It's fine? Okay. So let's now try to understand this part. So battery also has a rich, again, innovation. I will try to motivate you few questions by asking these things, and then perhaps I will focus more on flow battery. So this is what it has been plotted. Why to store electrical energy? That's a simple, very layman's questions, essentially. Here you see that power in megawatt and time. What has been plotted here? Storage of generated energy. If you start using it, eventually as a function of time, you reach to a very low number, right? You utilize everything, whatever is available, if there is no battery. And power generated, power consumed and generated, there is no storage. Okay, here and then if we have a power generated with storage, you see that this can be remain constant. You use as and when required, and you generate next day morning again. So batteries have to really store those energies, and it's a very conceptually, battery is a device. Again, if I read out a bookish definition, what is written in a book, what it says that it converts chemical energy in the electricity you need for the Kolhapur entire city. There is a data available always with municipal corporation. So you perhaps may not know, but people know that how much a power usage. Okay, considering the industry, considering the power in household, they have also distribution where people use it a power, right? Have you any time paid attention to your electricity bill, or your mother goes and pays, you don't care? Have you looked at it? What is the per unit cost? And recently it has increased. You don't care, right? Most of you. Why should I care? My parents are paying it, right? So, but you should, I think this is where I think, you need to really pay attention. Recently they have increased the cost all of a sudden. You see that our electricity bill, I think perhaps it's a good exercise. That's I keep telling my children, you have to go back and do some, analysis at house. You turn on the geyser, how much electrical power you need. That's where you start respecting all inventions. Otherwise you just go and press a button. I don't care. Okay, if I get hot water or cool water, doesn't matter. But everything costs money, and that's where your research motivation comes from. Saying that, okay, I need to address this problem, right? Let's say when I was a small child, we had a one television in our village, right? It was a massive television. It's a CRT, big. You can't lift from one place to the other place, right? I think you guys must have not seen CRT. Or someone has seen CRT? No. CRT is a cathode ray tube. It's a big, tiny one, but it requires tremendous amount of power to turn on the CRT. Now you see today's television. It's a very small, tiny one, right? But you see what happens over a period of time. So it requires again less power. Television doesn't take much power, but cathode ray tube used to take a lot of power, right? So this is the way invention happens, but eventually what the point I'm trying to emphasize more and more about it, you need a different kinds of battery at different places. Okay, I did not realize that this has come. Okay, so this is where I will walk you now. What is the importance of battery? Storage make resource management efficient. Okay, you can do as and when required. Helps greenhouse gas emission. This is a very broad statement, but it is in the context of environment, it is important. It provides energy security. It also gives energy management and quality power supply, and it meet distributed energy demands. Okay, so that's where so this is a very slide I prepared yesterday. I spent some time on making this slide. So here is the battery. What's a historical perspective? While preparing this slide, I learned so much. I think I spent 2-3 hours of understanding how Volta made the battery first. It's a very old history. Here you see that Alexander Volta made a battery here by using stacking of zinc and copper metal disc. And this is the electrochemical reaction. he could extract the power of 1.1 volt. Later, Daniel cell, I think maybe Daniel cell is in, everybody has read it in Master MSc, right? The Daniel cell has this salt bridge here, and this is by using zinc sulfate and copper sulfate. Again, so this is the aqueous battery again, and he used voltmeter. He used 2 different electrode. And then this is Gaston Plante. He made it 1859 lead acid battery. On all the, today if you go, today is a lead acid battery everywhere. All your UPS, whatever you see that. I'm not going to describe the very rich chemistry. Chemists should be very happy about talking about research in chemistry battery, because everything has an electrochemical reaction here. So we have to essentially, okay, and the Georges Leclanche, this is the guy, French guy, he made batteries with a different material. So people indeed explore the battery research in the past, and batteries are ubiquitous. So this is the important statement. Why do I say they are ubiquitous? You see, this is the recently Ola in 8th. Okay, I'm back again. I think you are trying to get rid of me and come back again. Okay, so all right. So these are basically the ideas are here. You see that this is the major challenge. I will talk a little bit more upon it. And batteries have been used also in this is in space application. Okay, space application. If you look at, I don't know, we all Indians are extremely proud with the moment we had very recently about Chandrayaan, right? You see that these are thin film solar cells. They are not made indigenously, unfortunately, but however they integrated very well. And there are also batteries there. So here the environment is again going to be very, very different. So batteries has applications not only on the planet as well as in space applications. So that's basically the idea. Battery people use for launching rocket. This is not a good sign by considering the situation all over the world. But however, you see that batteries people use it for even launching rocket. They need tremendous amount of power. For launching rocket is not an easy thing. Of course, phone actually we all of us have it, and when we are using it. So here the idea is use different kind of battery for different applications. You don't use similar battery here, this place and this place, because the capacity of required voltages are very, very different here. So you don't use similar battery. For cell phone, you use a tiny bit of a small lithium-ion battery. But however, when you need a battery to charge this one, 800 kilometer run from, let's say, Kolhapur to Pune is how much? 400 kilometer? 250, sorry. Okay, 250 kilometer. So you need how much gasoline for run the car, right? Like gasoline per liter, like 10 kilometer, 15, depend upon the type of a car. So you have to really, convert those numbers. And currently people are facing, for example, how do we charge our car? We stop at a gasoline engine, any petrol bunk or and we recharge fuel in the car. But however, if I want to charge battery,